Hello, I have already joined. I am already on the session 2. Yeah, yeah. हाँ आया नहीं ना. हाँ सेशन 2 में हूँ मैं. चलो मैं फिर से ज्वाइन कर लेता हूँ. सेशन 1, सेशन 2, 3D प्रिंटिंग एंड 3D विजुअलाइजेशन.
Yeah, ladies and gentlemen, thank you so much for this for the start of the next session, which is going to be very interesting. While the session is called 3D printing and 3D visualization, the crux of this session is going to be on new technologies and innovations done by these senior experts who have been in the space for some long time. May I introduce you to Sir Swarup Chand, who is the director for Endotech Information Systems, somebody who has actually been in the helm of 3D printing technology for almost last more than a decade and more, I believe, for his expertise in understanding how CAD/CAM design and could be taken into consideration. But the company is almost 3.5 decades old. But 3D printing is, Doctor, if I'm not, Surabji, if I'm not wrong, maybe 15 years from now that you have introduced this technology. And somebody who has got a vast experience and also a lot of solution building in terms of materials that he will also be sharing on the subject, and also the various different technologies, may it be on polymers or also in metal, and also on materials like carbon fiber. So I'm sure it will be a great, interesting session. Followed by him would be another gentleman, Mr. Chandan Mishra, who will also join in soon, who is from Lodestar, offering solutions in DMLS technology and also EVM technology currently. And then I have also, yeah, Chandan is here already. Yeah. So the Dr. Christ Paul, who is actually a researcher and a material scientist, done some great work and very impressive work that he's done in the educational space. And very interestingly to also know that he's also built an indigenous EVM technology machine. Doctor, thank you so much for your presence and your participation. I'm sure there'll be a lot of learnings for us to know. And also he's published a book on additive manufacturing. I'm sure it will be a great learning for all of us. And we'll also be promoting it through our 3D Graphy News, which is a new initiative because with last 7 years of our time and effort spent in 3D technology, now it is time for us to also do a proper proliferation with the content that we've been able to generate. So thank you so much, Dr. Christ. Paul,
Thank
and
you.
also Chandan is back. Chandan, a short introduction again, since I did introduce you, but you joined just now. So Chandan is the director for Lodestar Innovations. Primarily, they also deal into different technologies, maybe peak material. They are also into EBM technology and also DMLS technology. So they are also key respondents for these high-end machines proliferating and marketing in the country from companies like GE Additive and also Shine 3D and also Instames. If I'm pronouncing it right, a Peak Chandan machine. Then I have Shriyan's Court, who is yeah, thank you. Shriyan's Court is an AM expert, but his past experience is work with Bharat Forge, also a manufacturing center of excellence, and now with AIMS Solutions, which is also the first indigenous manufactured 3D printers in metal. Interestingly, they are also taking a great leap in the prospect of being one of the indigenous companies in India who has really made us proud. Thank you so much, Shreyan's Court, for being a part of the session. Also, then let me introduce, and with great privilege, also one of our key 3D graphy advisories in our panel for engineering, Group Captain Rajappan, who is also a key respondent and also a service provider. He also has a setup in Bangalore offering services in 3D printing. So he would want to also know which are the new technologies that is there instituted in the country where he can make a choice. Currently, he is using EBM tech. No, not EBM. Sorry, he is using SLA, doctor, if I'm not wrong, and also FDM.
That's correct. SLA and FDM.
FDM, great. So I think it will be a great session for everybody to know, understand. He comes from the end user's perspective also, because he's also an end user and now also a service provider in the aerospace and even shipping. We see a lot of prospect in building there too. So thank you so much, gentlemen. And may I now invite Mr. Sarup Chand to kindly take us through his presentation. Thank you so much. Thank you.
Sure. Good afternoon. I think people didn't have the lunch, so I don't know how they will be able to do that.
Right. So we are trying to negotiate in between sessions wherein people can also have a quick grab. I'm so sorry about that because we had a cascading effect, but I'm sure the content and the information that we had from the morning would have really kept them glued, and I'm sure they will manage it. Thank you so much, sir, and we'll start the session. Thank you.
So can you see my slide?
Yes, Saruji, I can see your slide, but you will need to come in the full screen. We are only seeing the.
That I would do.
Yeah,
Just hold.
thank you so much.
Okay, can you see it now?
Yes.
Fantastic, thank you. So I think in the morning session, we had some of the very good uh, talks by very experienced people like Dr. Anil Kumar, Dr. K.V. Kuber, Dr. Anthony, then Dr. Manjunath, and the last one was by Dr. Varmani. They were fantastic talks. They gave real life experience as to how they're using the technology in their day-to-day applications and how they have been able to use some of the best areas in material as well as in the area of design for additive manufacturing. At Roytech, as a group, works in the emerging technologies, and way back in 1989, when we started introducing the CAD CAM, the drafting board was known, and it was a challenge to change over. There's a lot of noise coming. There was a drafting board, the concept of drafting board for CAD has to be explained. The concept of a large board to a small screen being more useful that to be explained. Today I see that in this emerging technology of 3D printing, we are almost going to the same where the conventional manufacturing is now being added with additive manufacturing. We are close to about 30 years old. We have got 300 plus people working with more than 10,000 customers, uh, and we do provide work in CAD/CAM and conveyor in the area of additive manufacturing as well. Today, we have four streams of emerging technology, which is robotics, IoT, 3D printing, and adaptive CAD, which is an extension of the CAD system to a knowledge-based engineering, which are all the components of an Industry 4.0 or a smart manufacturing. As a company, we provide solutions and we have the equipment, and therefore we offer the services. It is in FDM, SLA, MJF, which is a new technology which has not been talked about in the morning. So I'll just touch upon that. DED and ADAM technology. Again, a technology which has just been introduced about 3 years back, and therefore some of the speakers did not touch upon that. We work in materials like polymer, resin, metal of different type. We work extensively with clay and ceramic, as well as the continuous fiber for carbon composite and other composites, and the bioinks. If we look at the technology and the value add, we do the reverse engineering as well as doing the 3D printing, which gets supplemented with design for manufacturing. Having said that, what 3D printing is doing, and I don't need to illustrate that, replacing some of the large factories running into acres to a factory which is within the room. Uh, I think most of the speakers have already spoken about some of these things, and therefore I will not touch upon because the time is relatively short. Reduced manufacturing time, no tooling, no MOQ, trial of alternatives, lightweighting, integration of many parts, complex geometry is the biggest advantage for 3D printing. And of course, the speakers did talk about the challenges in the area of finished parts, but a large part of the factory and the automation is done in tools, jigs, and fixtures, which as of right now does not require that much of certification and is a low hanging fruit for additive manufacturing to be adopted in the different area, whether it is for maintenance or it is for the parts to be assembled or quality checked. So you do use it for prototyping and working on alternative functional design. And I think Dr. Manjunath illustrated it very well in the morning session on how he's able to use or his team is able to use the visualization to facilitate the manufacturing of the engine as well as the different components of the engine and improve upon the design. And he I was very impressed with the design with the visualization model where he talked about the weld guns being chosen and optimized on a plastic model so that there is no interference which happens and the part could be manufactured. So I think prototyping is not just for the part visualization but also to test the jigs and fixtures as well as the manufacturing process per se. In terms of functional part, there could be operational parts, which is what was discussed in the morning. But there are a lot of ground facilities related to communication systems, exoskeletons, nose cover for missiles, battery casing, radio communication systems, which are not the functional part but are facilitators on the ground facility, whether it is a satellite to be launched or it is a space station to be worked upon or a defense equipment. So when we started working with some of the people in Air Force and Army, even simple thing like jigs for holding and opening the or filling the selenium in a missile are critical components and are required to be made because they are right now being imported. Uh, Looking at the growth, a lot of people have now started working on it. So it's not an effort anymore of one organization which is making everything like it used to happen in a DEC system or an IBM system where the hard disk software, the computer board were made by one guy. Today, it is being made by it. It started getting democratized, and in the same way, 3D printing is taking a big jump, where the technology provider, the software people, the simulation people, the material suppliers, the service providers are all coming together to give that growth from that peak trough and then going up. And if you look at it, very large manufacturers, technology providers, very large mm, material manufacturers are all now working to see how they can be a participant in the future of the manufacturing. And additive manufacturing is one of those future which is being seen by all these companies, which I think will help in taking this additive manufacturing to the next level. I don't think I will be. I initially thought that I will talk about technology, but I'm skipping this because I think most of the people are familiar with the technology, and I don't need to touch upon at least the conventional technologies of the FFF or the SLA printing, and I'll skip this. So I hope it's okay with everyone. Metal was discussed in the morning session extensively, where the advantages of the DED, wire EBM, as well as the powder-based technology was discussed and was shown in terms of illustration as to where the powder-based technology become more applicable than the direct energy technology, direct energy deposition, or the wire EDM, or a beam technology. All were discussed, so I'm not going to. I think, if you permit me, I'll try to skip this as well. What was not talked about, and I think I would touch upon that, is a new technology which has come up called the Atom technology. In the Atom technology, if
Hey
you look
everyone,
at
I'm
it,
here to talk today about the Mark
can you
IV's
hear
Metal
it?
X process. It's a simple, safe, and cost-effective
Yes,
method to go
yes,
from design
Pitarji.
to functional metal part. There are 3 steps in this process: printing, washing, and then sintering. First, let's start with CAD. You design your part, then export to STL and upload it to Eiger. Eiger is a cloud-based slicing and print management system that comes with every Markforged product. This automatically configures your part based on the material and printer you've selected. When your part slices for metal 3D printing, it gets scaled up to account for shrink and deformation in the downstream processes. It then slices your part into discrete layers, identifies overhang features, and builds supports and a raft underneath your part. As we go through printing, washing, and sintering, Eiger will monitor the part's progress along the way. Let's start this print and go to the Metal X. Before starting a print, the machine automatically maps and levels the bed to ensure the first layer goes down well. Your print is built of 2 materials stored in this heated chamber above, one of ceramic release material and one of the metal to be printed. This filament material is metal powder safely suspended within a 2-part plastic binder. It gets heated and extruded onto the build plate, where the part is created layer by layer. The release material gets extruded as an interface between the part and its supports, so that once your part comes out of the furnace, it's easy to remove. Unlike other metal 3D printing systems, this process does not require loose metal powder, resulting in a safer and more cost-efficient workflow. 17.4 stainless steel is loaded now. However, with a quick changeover, the system is capable of printing in stainless steels, tool steels, coppers, Inconel, along with several other materials currently in development. Once your part is finished printing, you'll get a notification. At this point, you can go to the printer, remove the part from the build tray, and clear the bed. Now we have what's called a green part. It doesn't really look or feel like metal. However, a large part of it is comprised of metal powder. Next step will be putting it into wash 1 for the debind process. The wash 1 removes the first stage of the binding material. A green part is taken from the printer and placed into the wash basket, which is then lowered into the solvent. Wash times will vary, ranging from a few hours to a few days, depending on the thickest region of your part. After that, it's now called a brown part and is ready for sintering. Let's go over to the furnaces. This is Sinter 2, a furnace designed for mid-volume production runs and larger printed parts. Sintering transforms a print from a lightly bound collection of metal powder to a fully finished metal part. First, the temperature ramps slowly to burn away the trace amounts of remaining binding material. Then, temperature ramps closer to the melting point of the material, allowing metal particles to start to fuse together to create a strong metal part. Mark IV sintering furnaces use a carbon-free retort to ensure part quality and alloy composition standards are met for our finished pieces. Each run takes about a day and can be monitored remotely using the AEROSPACE software. Once a run is complete, the setter tray full of finished metal pieces can be removed from the furnace. Once removed from the raft, these parts are ready for use. In the furnace, the layer of printed release material between supports and the raft and your printed part remains powderized. This allows the structure to be tacked to the raft to better control shrink and accuracy throughout the process, but also an easy release after sintering. At this stage, your part is fully sintered and ready to be used. It can be post-machined, polished, or otherwise processed as necessary for the final application, but in many uses, the accuracy and strength are good enough as is. It's ready for install. Check out markforge.com for more information about our simple, safe, and cost-effective method of metal additive manufacturing.
I hope this gave you an idea of what I meant by a new technology where you didn't need the CNC machine, you didn't need the wire EDM, and one of the speakers did talk about ready to use parts, and it does not require you to have the difficulty of changing the powder or changing the metal for different metal parts to be printed. So on within a minute, you can change it over to copper or to inconel or to any other material. So we think that this is a game changer for various applications for producing the parts in metal. So it does not also lead to any powder flying when you have to take out the part. It does not require too much of cleaning up of the parts, as well as sintering, as well as the debinding process is a clean process. So today you have even tools, filaments in A2, D2, H13, apart from the stainless steel, copper, and inconel. The second process, which was not discussed and I thought would be very relevant, is the so far only the laser spot was used to do the melting of the polymer and making the parts in polymer. There was a new technology which was introduced by HP called MJF technology. In the MJF technology, like inkjet printer, you are no longer typing one dot by one dot by one dot, but you are able to do 16,000 dots in one go, which means you almost do printing as if it's a full page printing which is being attempted. If I share with you how it is done.
To reinvent 3D printing, HP engineers went to the very core of 3D printing science, the voxel. Think pixel, but in the 3D space. Unlike conventional 3D printing, transforming part properties voxel by voxel allows for fully functional prototypes and final parts today and limitless applications for the future. HP Multi-Jet Fusion applies proprietary liquids onto the printer bed at 340 million voxels per second, each measuring 1/3 the width of a human hair. Next, our proprietary heat fusion process affects the structural properties of each voxel, resulting in precise detail and advanced mechanical properties. Our agents, print bar, and heat fusion process make multi-jet fusion a totally new 3D printing technology, one that delivers consistently high-quality parts, faster, all at a lower cost. And it can all be scaled to produce larger size parts or more parts per day. That's the kind of tangible proof industry needs to reinvent manufacturing and shift away from traditional methods. And shifting, they are. It appears the next industrial revolution is in full gear.
So I think this gave you an idea of how the polymer printing can be done very fast and can reach the production level. So today we produce from our service center at least about 2,000 parts per day. So that gives you an idea of how much production can be done, small parts. If there are big parts, during the COVID period, we produced in about 30 days time, more than 2 lakh parts which were used for the ventilators, they were airtight, they were watertight, and they could be directly used because they were accurate and had good enough finish to be utilized. So the third technology which was did talk, Dr. I think uh, and Mr. Anthony did talk, Dr. Anthony talked about it, and then this is a technology of carbon fiber. Now, carbon composite are very, very strong. Shibu, can you hear me?
Yes, yes, you're audible.
Okay. And the videos were also audible, no?
Yes, yes, yes.
Thank you. So the third technology which is there is while the composite can be a mixture of the matrix material like nylon or petri or any of them, and then in that you mix up very microfiber of the carbon to make it a carbon composite. But the strength though get improved over the ABS or petri or peak, but it does not give you the strength of a continuous fiber. Like in a concrete structure, you reinforce it with steel bar. In a plastic part, you can reinforce it with different type of fibers. These fibers can be carbon fiber, they can be Kevlar, they can be glass fiber. Depending on the usage, you use these different type of fibers to get that significant strength, and the software allows you to do the orientation of the fiber in the XY at any angle, and therefore you get in the XY a very strong properties in any of those directions. So if I can show you, if you look at it, this is the printing which is going on. The same technology as was shown in the metal is also used in the carbon.
To understand the profound impact of being able to 3D print metal parts like these, just look around you in the world around you.
This is industrial. I mean, this is a different scale.
With Markforged, every year is like a new breakthrough.
With this new printer, you print materials you already know how to use. There's no learning curve.
Sorry.
You can bring that magic right into your office. You start to print tonight, the next day you're.
So you can print continuous fiber directly on the printer, and you can lay it up in any direction which you would like to do. So that gives you the capability of making very, very strong parts in the plastic or in the carbon composite. The fourth technology, which was also not talked about very much, was the SLA technology. I think the Formlab did a fantastic job from their earlier version of the Form 2 to the Form 3, and now the 3B as well as the 3L, which is a very large size printing. What they did, they improved the tank to make it a flexible tank. As a result, the parts don't get pulled out from the build plate. And secondly, they made the laser enclosed. As a result, the problem of resin going and hitting the laser does not come in. And it gives the high reliability. So if you look at it, this is the curved bed which was there, and as the plate moves, it becomes 90-degree, and since it becomes 90-degree, you are able to get far, far higher accuracy. Today, you are able to achieve 25 micron accuracy on this. And they introduced a large number of resins which are suitable for high strength, high the clear resins. They introduced bioresins which are fully biocompatible. They introduced resins which are flexible with 50A or 80A shore, so you can make rubber-like components, and they are used as a rubber-like components. So with this, they are able to achieve a very high accuracy, and today it is being used both for jewelry and for dental. Practically 90% of the jewelers and the dental people are using the Formlab for different applications. Of course, there was a touch upon the bioprinting, where the bioinks are also being used for doing the printing, and we work with bioinks extensively and work with various institutes as well as the medical organizations in this area of pharmacy and to print the tissues. So this is one of the printers which we are manufacturing ourselves, as well as we are giving it to the different institutes for different applications. So in this, what we did, we introduced a concept that instead of having different type of machines being purchased, you can have one machine and in which you can change the extruders to be able to make a syringe-based printer, which can be used for silicone and material like this. On the same machine, you can print peak, and you can also do the engraving or the cutting using the laser. You also have a CNC tool head, so you can do a little bit of its CNC work as well, apart from doing the work of printing the polymers and things like that. So these are the different type of materials which can be printed using this type of a technology. And these are the type of extruders which come. So we even printed the epoxy by combining the two materials in situ, which is a critical requirement for printing the epoxy as one of the layers during the print process. So having said that, today the materials which are available are very large range, which is metal, resin, nylon, thermoplastic, including high temperature thermoplastic, fibers, carbon fibers, and ceramic. We work with all of them. And I think Dr. Burmani also touched upon the design for additive manufacturing and the significance of design for additive manufacturing. I think this is one of those examples where it was used for lightweighting. And I like to touch upon one issue here. One of the key advantages why we do lightweighting, apart from the temperature, conductivity, as well as for the purpose of different needs, is it reduces the cost of doing the printing. And since it reduces the cost of printing, our production run, many of the parts, when done with optimized design without compromising on the functionality, my cost of part comes down. So there was a company which was making the LED lights. He came to us and we did the design for additive manufacturing. His conventional aluminum extrusion with paper insulation was costing him about 650 rupees. It started costing him 430 rupees once we did design for additive. And the same thing when we did it without design for additive manufacturing was costing him 2,200 rupees. So he would have just been happy with the prototype, but once you did the design for additive manufacturing, you were able to reduce the cost and were able to make it production run. There is another company which is special purpose machinery manufacturer. He had 300 components and he had an inventory of 6,000 bins in which the parts were being kept. Once they started using the additive manufacturing, all bins vanished because now they are free to make changes in the design instead of getting limited by the design, the part which is already available for the new design to be done. So design for additive manufacturing and 3D printing combined together is reducing significant inventory and cost if we adopt design for additive manufacturing judiciously. Some of the defense parts, if you just look at it, this was developing the flexible coupling with different designs and different material. So one of our preferred material was onyx combined with carbon fiber, continuous fiber for high torque applications. And in this case, we were able to get as much as 750 nanometer torque, which is very, very high. Typically, it would have been done in stainless steel or would have been done in titanium. So we use the carbon fiber and the PEEK as a combination. Another example, I think I would have been very happy to show it to Dr. Anil Kumar. One of his groups worked on the pipe for the cryogenic engine, and we modified the process of printing where we used one additional axis, which is a rotating axis, along with the X, Y, and Z. So we printed it. Many of you are familiar with FDM process. The printing is done in the X and Y, and then the bed goes down and the Z get printed. In this case, we printed it on a rotating axis at any of the angles, and to make it isotropic, we also use the length, the extruder moving along the length, and by doing it, we were able to make the pipes which are PEEK with carbon fiber. So it gave a very, very high strength, and they are now doing the testing for the cryogenic engine tubing using the same technology. Another nice example, which I think is very relevant, is a battery box. And this is being used for electronic vehicle, for the drones, as well as for different vehicles being used by the defense. So you can use a combination of carbon fiber with PEEK and or any of the PSU polymer to do the battery boxes. Now we have even introduced the ESD material, so you don't have a, you can use the ESD material or a material which can be fire retardant material. So using a fire retardant material, you are relatively safe that there will be no flame, even if there is some short circuit, which can happen in a box in which the electronic is housed. Uh, Another nice example which we worked upon using an SLA technology and a flexible material with about 80A shore strength is the bellow. And this is a very large bellow in which it moves as flexibly as they could have done it, and it got done in less than a day's time. So imagine a bellow being made in a rubber-like material in 1 day time. This was again done for VSSE using this. So Dr. Burmani was here, and I think we worked with Honeywell to give a different type of graphene usage by them, and we used the graphene plus the metal powder combined together and worked on the 3D printer, which you just saw, where we could combine the paste along with the other things to be able to print it out. So you can create your own material and test the additive capability, which is ideal for a research institute or for an educational institute. Here are some more examples of hand jigs, lid plates, display cover for electronics, filament guide rolls, display cover for electronic applications using the fire retardant materials, or the impellers for the, in fact, in one of the machines, they took it to the ship and used it for making the parts. So I'll share with you that example as well. In defense and army, typically you need ruggedness and for the parts. And I think the onyx with carbon fiber or the PEEK gives far, far higher strength. And now we can combine PEEK with carbon fiber to be able to achieve that. An example of it is that when a vehicle is moving in the night, you need the hatch plugs to be able to see inside the vehicle as to what is ahead. So these are night cameras. This was typically being made in metal. Now using the carbon fiber, this could be done and the cost could be significantly reduced from $800 to $230. This is actual example of a US Army being using the same. So I'll skip this. Uh, there was another example of a US Marine trying to test the different type of uh, uh, bombs and making the outer casing with the help of the carbon composites. I think what is critical as a technology is not just for usage within the safe environment. Uh, Today, the demand has started coming both from the Indian defense forces, as well as it is also being used by the US forces, where the machine had to be made such that it is mid grade, and it is the packing is such that it is satisfying the Pelican AL3232 single lid mechanism, and the machine could be carried, the parts could be carried, the components could be carried, and the manufacturing of the parts could be done both on the ship as well as on the vehicle directly. So you didn't have to create a separate room for doing the same, and therefore the Mark Forge, as one of the companies, worked on the same. And today you have the machine here, you have the components, you have the spools, and you have the casing in which the machine does not move, and you just start using it from whether you are using it on the vehicle or you're using it on the ship or you're using it on the aircraft. Uh, all of us have talked about the mechanical applications. I thought that it is equally relevant to talk about how the 3D printing is being used now for by some of the Indian armed forces to make what used to be called as a model for doing the planning of the defense forces movement. So using the satellite image, you can get very accurate 3D model of the terrain. And with that, one can do line of sight planning, one can do the logistic movement and other applications. Uh, the second application which was talked about is that can we make the full electronic, including the PCB material, which is dielectric, which is critical for making the antennas. And especially when you're talking of 5G and 6G, these antennas become very relevant. And they are very, very small in size. So using the 3D printer, you are able to make 32 layers simultaneously. And instead of mounting the components on the top and the bottom, you could mount them inside as well, because using 3D printing, you can leave the cavity where the mounting need to be done. The capacitors, resistance, can, or some of the passive components like inductance, can directly be printed using the electronic inks. So today you have the conductive inks which are being used, as well as the dielectric from which you make the PCB, and you are able to make a very dense component part very quickly as a single component, so you don't have the dry soldering as a common problem, which is a common problem which happens. Another application which I wanted to touch upon and which we work with is the civil engineering space, is the use of clay and different sand to make the 3D printed parts. Why is it necessary for defense? I saw one of the applications which the defense forces were using in the Middle East during the war was to create T-walls and uh, protective barriers, which one could also use. And they use the 3D printing very intelligently, where they use the curved uh, walls, and in between they left a hollow this thing where they put lot of golf balls, because golf balls are very hard, and they change the direction of the force which is coming from a bullet or from a bomb. As a result, they became much more protective, and at the same time, the thickness and the weight of these protective barriers was far smaller, so far lesser. So you could use in the defense forces applications which are little offbeat, which do not require so much of classification, which can be certified a lot more easily, and they are low hanging fruits in the defense forces. I also thought that maybe because over a period of time, the drones is becoming a common requirement in every area, whether it's carrying the medicine or food, or it is to carry some of the weaponry as well. So Today, we as a company have been working with a lot of drone companies in making the different components, which would also be necessary for the MRO as well, because these components need to be replaced. So if you look at the complex structures which have been worked upon for the camera, for the structural elements, for this thing, and embedded with carbon continuous fiber to give them the strength and work almost like an aluminum part, right? So in brief, this is what I wanted to share with you, and I thought that maybe it gives you an idea of how the technology is moving and how we as a company, as a Droidtech as a company, can support you in doing the proof of concept, in trying out the different parts, and trying different technologies, and how at the design level we can participate along with you to be able to do the proving and then subsequently doing the production without you making that much of an investment. Thank you very much. Hello?
Yes, Saurabhji, thank you so much for your insightful presentations. I think it covered almost all the aspects of what can be offered when it comes to resin or metal or thermoplastic. So you covered a very, very broad spectrum in terms of the offerings that you also have in services. So it was very interesting. Now, if anybody has questions to post, please you can ask questions, and probably Saurabhji can respond eventually as we progress to the event before the panel discussion. Saurabhji will also be joining the panel discussion today, where the schedule has already been posted in the program. We had to change the schedule in terms of time, so we will try to maintain this timelines accordingly. So I think any questions we can also discuss with more key respondents joining in the panel discussions also. If there are any questions, we can quickly respond, or we'll go to the next speaker.
I don't think there is any question.
Okay. Thank you so much, Saurabhji. And may I now introduce Shreyan's quote from MA's Solutions Private Limited. They are also an indigenously manufacturing company, manufacturing 3D printers, and they've been in the additive manufacturing space for, say, close to 7-8 months now. And Shreyans is actually responsible for their AM division. Thank you, Shreyans, for your time, and we can start the presentation. Yeah, thank you.
Anybody can see this? Everybody can see this, my screen?
Yeah, we can see your screen, and we can start. Yeah, please. Thank you.
Thank you, Dr. Shibu John, giving this particular platform to present our machine, Make in India machine. And then we will start with this particular S Mathematic Group company. What we belongs to the group. We are hardcore machine builders. This particularly started with the Micromatic Granting in 1973. Founded by technocrats, all are technocrats, and then we slowly moved to Pragati Automation, which is the largest CNC turret manufacturing in the second world largest CNC turret manufacturing. And then our flagship company, Ace Designer, which is mainly in CNC lathe manufacturing in the turning solutions. This is found in 1979, and subsequent Micromatic machine tool. This is a sales and marketing company for all these group companies. This is formed in 1987. And then AMS, the ACE Manufacturing Company, we are formed in this particular for the machining solution for this VMC, HMC, and then 5-6 machining. Total group till date, we have the capability of 10,000 machines per year we are producing. And then till date, more than 95,000 we have machines sold across the globe also. And then we have some IoT industry 4.0 and IoT company, which is 2002 we have formed. And then apart from these, we have some casting, forging, and machining companies. And then 2018 we formed this AMS solution with a joint venture between ACE Designer and AMS. This is called as AMS, called as AMS solution to make in India machine only. Because we are hardcore machine builder, we are a motto to sell this particular machines. This is my agenda of this particular today's meeting. Why additive manufacturing? Already all these particular speakers, they have already covered this, and then AM for aerospace, and then process validation. Okay, I will do this particular presentation for process validation and some case study, and then about AMS, what the AMS machines we have designed these particular things. So 3D printing is one of the disruptive technologies. If you compare this all these particular IoT kind of things, cloud technology, energy, automation, robotics, how we can leverage this particular capability of 3D printing. It's up to you, up to us only. This has some advantages and some hypes are there, but how we has taken this particular additive manufacturing to leverage the advantages. One of the advantages is already they have already previous speakers they have explained in details all the advantages. One thing I wanted to point it out just now. Vaman Kulkarni also told you that DFM. So what are the designs are available in the market till date? Till date, what are the designs? You can take any designs whatever the designer thinks previously by keeping in mind what are the manufacturing processes are available. Means previously there is a casting, forging, machining, fabrication, welding, brazing, etc. etc. All the processes are available. According to the processes are available, he has designed their own design by keeping in mind the processes are available. Nobody thinking the advantages of additive manufacturing. There is a complexity parts we can produce in this additive manufacturing, part count reductions. So we have to add the value. We have to add the value by design for additive manufacturing. So there is a separate topics are there. Basically, this is the aerospace defense industries are there. So there is a weight reduction will definitely give this particular carbon footprint saving on this aerospace total weight of the aerospace. These are some examples are there. By putting the topology optimization and lattice structures, we can reduce down this particular the component weight, and it can be possible by 3D printing, manufactured by possible by 3D printing. Second will be the part cost reductions. Already so many speakers have shown this particular GE catalyst engine, and then if you see the cost effective manufacturing by per kg weight from automobile to aircraft design to aerospace, if you save this per 1 kg of engine, the huge amount of this particular monetary benefits are there on the 30-40 years of life of this particular aerospace aircraft, and then subsequently to reduce down the carbon footprint also. And then there is on-demand manufacturing. We have some case study. I will show you in the next slide what are the on-demand manufacturing, how we have given this particular services to URSC for their Chandrayaan mission also. Second will be the AM for aerospace industry. And then what are the product lines are there? This particular gas turbine engine parts are there. According to engine parts, there are so many engine parts are there. There is a stringent requirement to qualify this particular engine component by additive manufacturing. So many certification bodies are there, FFA, SEMI, already mentioned by Vaman Kulkarni sir also. But the particular certification requirement for different companies is different. Rather than going to rotational engine component, we have to concentrate on the internal structure also. There's a two different scenario for aerospace also. If we concentrate on the aero ducts, there's particular seat framework and seat and cabs, wall panels, so many are there. There is a part screening softwares are there, or we have to part screening. What are the daily available particular component? How we can twist the design, how we can do the complexity, adding the complexity, and then how we can add the value by topology optimization, part count reduction, and it can be best suitable for additive manufacturing. what are the different technologies are available in the additive manufacturing. We have to think, our designer has to train like that only to how we can convert conventional manufacturing design rather than there is some stringent requirement for engine component. Let's see, first we start with internet structure, then slowly we can move to engine components. To validate particular process, my intention or my experience is that rather than going to particular stringent requirement of aerospace component, we have to qualify our process itself. Means how we can qualify the process itself. Once we started with our starting from the powder to simulation and then printing parameters. Then once we qualify, means standardize our particular process itself, definitely it will easy for us to qualify all the certification levels, including FFA, semi-lac, all kind of tests. So starting with the powder, we have to check with the powder what are the manufacturing of this particular powders. Either it is a water atomized, gas atomized, and then EGA and then plasma atomized. We have to check with this, and then we have to certify this particular powder by particular testing, in-house testing facility. We have to develop our process to qualify this particular powder by particular apparent density, and then checking this morphology and phd also, and then some kind of what kind of internal defects are there, agglomerations are there, particle size distributions are there. We have to check it, we have to establish it, we have to print some coupon, we have to document it for the traceability point of view. How many times this powder can be used? Means if you take the SS316 or if you take the Di6 alloys, how many times I can reuse this powder? Means first use powder, second time use powder, 11 time use powder. We have to test this coupon by density, microstructure analysis, and these particular mechanical properties. Then once we have some particular structure in-house itself, we will definitely, it will be easier to go to any certification body rather than ASTM, semi-lac. Once we have this documented information, we will definitely represent, and then anybody can represent it and go for the certification kind of things. Second, we will come into the particular laser process parameters. How there is a, if I'm not wrong, for powder bed technology, 244 or 260 parameters we can vary. Mainly, this some I have identified here. This particular power scanning speed. Apart from this, there is a fill counter. There is a border. N number of borders we can. Then down skin, up skin. We have to play with all kind of things. Third will be the process simulation. Now in the market, if I'm not wrong, the semi-fact is available. Then NetFab is available. Then the Altair is available, and then N number of simulation software is available, where we can check the distortion level, temperature distribution, and then stress analysis. These are the predictive software developed by this particular algorithm. We have to print it before the small test coupon, and we have to fill this particular distortion level. So it will cover the almost 91 to 95% predictions. Then we have to check the prediction level to qualify this particular before going to print this particular part. Once we have this particular distortion level, definitely we can add the supports wherever required to avoid the distortion, to avoid the heat dissipation, means to give the good heat dissipations. Next will be this particular mechanical properties. There is a standard procedure we are following, we are following is this particular microstructure analysis. Tensile coupons, we have to print it if required. If required, creep test, fatigue life improvements, fatigue some sample, low cycle fatigue, high cycle fatigues with high temperature, low temperature, and then impact test also. And then second will be this particular, we have to check this particular microstructure analysis, and then the hardness levels with particular predefined points only. We have developed our own standards to qualify our factory test acceptance machines also to qualify all these particular tests. Second will be we have to check this particular entity test also. What our process, but combination of powder, combination of process, combination of laser process parameter, and then the heat treatment what we have given, we have to check this particular porosity level. There is some instruments are available, even also software prediction softwares are available where they can predict by combination of these with combination of material properties. What are the TTT diagram or CCT diagram, that particular material, and with giving the heat input by laser power and scanning speed, they will predict it. And there is testings are available. We have to check this particular density level or porosity level, and then we have to correlate this particular with the process parameter with the post processing, what kind of heat treatment cycles we are given to this, and what kind of expected is 99.99, 98.99, what are the density level and the porosity level. And then we have to go this particular crack levels also. We have to check with the NDT levels. Third will be this particular as per the ASTM standard of 52902 and then 52941. There is a standards. Now they have published kind of things. We have to go for the dimensional accuracy of this particular machine. What we have developed our machines, we have to qualify our machine also. To sell with this particular aerospace market, we have to qualify our machines also. Therefore, this particular small intricate shapes, holes, which can be produced. There is some standards are available. Below 45 you cannot produce. Below 35 we cannot produce. These supports are required. How our machine laser and scanner combination give the smallest printing accuracy, we have to qualify. And there's some standards are available for design and materials process and terminology and test methods. We are following these particular standards for our machine qualification and process qualification. What are the product printed in our machine? We have to establish particular this particular processes itself. Third, I am jumping to the case study directly because I had to more concentrated about the machine what we have designed and we have to showcase. Some case studies are there. If you see this particular first case study, we have printed in ALS at Amg for VSSC space application, and then if you see this small intricate shapes what we have printed, it's a delicate intricate shapes, and we have printed this particular what you call one part inside the another parts with this part consolidation, and then we have printed with this 17 hour cycle time. Main benefit will be the saving of tooling cost and reduce the lead time. Definitely, I wanted to focus that we have the capability of n number of material we have developed till date to bundle with our machine. Second, is a defense application RF waveguide. They have manufactured this particular component by sheet metal, and they have welded together particular things. There is a reduction over of the 100 parts into one single assembly. Definitely, this is not our design. They have modified this particular design with the inputs given from us and then multiple sources, and they have given the design. The more stringent requirement will be this particular leakage test, and then the support. Inside there is a support is coming. So we have done this particular orientation kind of things, and then we have added dummy walls to reduce down the supports inside this particular structure, and we are now, after that we have some slightly machined and we have supplied in the particular within the 24-hour cycle time. Third, this particular collimator we have supplied to URSC, collimator for satellite for ALS at TMG, and then if you see this particular the stringent requirement along the 110 mm length, along the length of 110 mm, we have to maintain this particular walls 1.3 mm. The laser spot diameter available in the market, what are the existing machine seller, they have the available in the market laser spot diameter in ranging between 50 micron to 80 micron to 120 micron. If you see the 120 micron laser spot diameter to overlap kind of things with the heat affected zone, and then the powder surrounding is sticking to the wall, it's very difficult to maintain the 0.3 mm. So we had done this particular analysis. Our researcher, we have done so many test coupon to validate the 0.3 mm with the surface finish requirement also. And then we had developed a special post processing method also to clean up this particular walls to give the good surface finish, and there is a no leakage requirement in signals. There is specific requirement, and then we have printed 40 hours, 4 parts in the 40 hours, and then in this particular ALSR10 Mg material. Fourth will be this again the defense application to it is what you call a body scanner in this airport. The instrument, electronic instrument placed into this particular thing. There is a casing for this housing kind of things. We have printed this particular in ALSR 10 mg. Previously, there is a they wanted to they are manufacturing by PDC tooling and then pressure die casting. If I'm not wrong, yeah, pressure die casting, and then within 36 hours we have printed 2 components. There is an urgent requirement, and then we have done some post processing equipment of anodizing on this particular ALSR 10 mg. Specific requirement of 0.3 mm thickness, 0.3 to 0.5 mm thickness of this particular anodizing requirements are there. We have established this particular process with printing, orientation, and then machining also, and then this particular post processing. This application is the thruster part. Recently, this is came from this particular Latin America. That's particular for aerospace application. And then there is a stringent requirement is there. If you see the inside, there is small intricate holes are there along the length. We have to maintain this particular ovality or concentricity of this particular hole. If you see SS316, almost 40% elongation material. Means after printing, we have to go to for this particular machining. It is a very ductile material, and because of chromium and kind of things are there, and then the support removal is a tedious job. We have to play with this particular process parameter to give the less energy density for the supports, because it is a hollow inside, and this particular holes we have to print almost 30-40 mm along the length. So it is very difficult to hold that particular parts, and secondly the support optimizations. So we had done this particular monolith structures, this particular with the faster time to the market, and now we have provided. Now it is gone to prototype application to batch production now, because we have qualified this particular their requirement, their specific requirement of that particular company. We have qualified. We have supplied this particular first batch, then the test coupon, the tensile coupon, and then microstructure analysis, and then particular some kind of phase analysis they are required. We have supplied very enough, and then now we are going to a particular for batch production kind of things. This is the exhaust mixture. We wanted to showcase this particular actual photograph of our Amaze machine inside the 400 by 400 by 400 with a twin laser machine with 1 kilowatt. Twin laser machine means it is a high productive machines. We have printed less than 17 hours all this particular big set components for this aerospace application, and then we wanted to try this particular internal alloys, because high temperature alloys, it is a high temperature alloy, to check this particular temperature distribution and how much temperature it can withstand. Some testings are going on still there, and then very soon we will this particular qualify this also, this particular not only product but the material itself. It is a metal qualifications are going on, and then complex structure can be possible by this particular things. Fourth one will be the just in time. Just now I told you in the previous slide itself, the 3D printing required once this particular URSC came into the company, we have supplied too many parts also. There is a Chandrayaan mission. Unfortunately, it has been failed. But once the rover will move this particular moon surface, in this particular last rover, they have put this particular emblem, Ashok Chakra emblem, where the impression on this particular moon surface will come into picture. And then in this particular just in time, within 8 hours, it is almost 2 or 3 hours printing plus particular machine cleaning and then the design validation because it has a curvature surface. It has split into 1, 2, 3, 4, 6 parts differently, and then we had to check the design feasibility, and within all these particular projects, we had delivered within the 8 hours. Means it is a just-in-time concept where we have added the value. We means additive manufacturing advantages. The process advantages are there. We have added the value. Okay, so this is the case studies are there. Now, time to show our this particular machine, what we have developed our machine. First machine, by keeping in mind what are the restrictions, what are this particular current limitations available in the market for the selling of this particular European machine manufacturer. We are keeping in eye, we have developed a 400 size machine. This is the particular high powered laser powder bed fusions. Means it has two lasers with 1 kilowatt each. Means in case if you want to go for productive kind of things. Currently, what are the other machine manufacturers providing up to 30 micron, 60 micron, 80 micron, maximum 100 micron. Definitely for production purpose, if you really want to reduce down the manufacturing cost of the product, we have to go for higher layer thickness. Higher layer thickness, definitely somehow we have to go for the higher power laser. Somehow. And then for this keeping in mind, even also high temperature alloys, by keeping in this particular inconel or tungsten carbide required high melting point of kind of things, we have to go for high kilowatt lasers. Second will be the large building volume with higher productivity. Third will be all this because we believe all 60 years what we have the machine building experience. We believe once we open this particular machine, more and more trust will generate. And then to taking all this particular thing into mind, all the laser process parameters, including all this particular power, scanning speed, almost 250 parameters, we are fully editable parameters with multiple materials, with layer thickness, and definitely our machines can be open for all powder sources. There is no restriction kind of things that this powder can be used, this powder, this particular material can be used in our machine. And then we have the less recoating time. We have the bidirectional recoater systems with the multi-blade technology, patented technology, with minimum recoating time. What we have given to this particular motor without disturbing the powder spreading quality along the 400 by 400, we have reduced down to minimum to 3 seconds. And some of the distinct features are there. Our machines, it is a smart powder manufacturing system. Means if you see this, if you want to really want to hide particular product for the aerospace, there is no stoppage is required, no machine pause is required. Once the machine will pause, the line marks will come and definitely it will disqualify this particular product. By keeping in mind, we have put some sensors, some particular, our algorithm, our brain, our innovative ideas, and we have patented this technology. The machine will give the alarm, or the machine will sense it, what are the powder available in the hopper, and according to the height machine part height, it will give this particular indication to the mobile and the particular screen also, how much powders are required, how much powder will go to this particular overflow kind of things, and how much you wanted to put after sometimes. Means if there is a 20 hours job are there, and then after 10 hours you have to put this kind of particular powder. So this machine can speak this particular kind of things. Second is a real-time monitoring and control of machine, like the IoT kind of things. Means what are the quality after printing each layer. The the machine take this particular picture and then particular deformation level and then heat mapping, all kind of terms. This machine can be do the real time monitoring. No need to watch continuously the machine how this particular problem happens. And if I take this particular 6 days build, and then after 5 builds we realize that something is happened on the day 3 and we don't realize, and the supports has broken down, this particular leaf has been broken down. So this particular disadvantage by experience we have taken care, and we have developed this particular real-time monitoring of these particular machines. And then we have this particular machine hand holding and support. Earlier mentioned in this particular first slide, for this all group companies we have dedicated one company, it is called as Micromatic. We have the more than 80-90 cities, we have the offices where 250 plus engineers dedicatedly looking for the supports and the kind of things. And then as you know, we are the hardcore CNC machine manufacturer. We will give you the complete end-to-end suite. Means from this particular design software, this particular printing kind of things, and then 5-axis and post-processing kind of things. It is a enhanced user-friendly machines. And then what are the subsystem class systems are there, or components are there? We have used all these particular standard components. I think some background noise are there. Somebody can note these particular things. So I can go ahead. Okay, thank you very much. And then what are the lasers? What are the scanners? Are used? What are those particular servo drives? We are used the best in subclass systems. And then faster ROI of the printing point. Definitely all this particular advantages clubbed in this particular machining. You can get the faster. These are the specification I already stated that 410 by 410 by 450 height will be the bigger, and then 1000 watt fiber lasers are there, and then the scanning speed is what the scanners has given this particular up to 9 meter per second we can give. And then layer thickness till date we are qualified up to the 100 micron layer thickness for this particular materials. And then beam focus diameter is 80 micron to 120. There's we are using the VARIOSCAN, where on the borders you can use this particular 80 micron to improve the surface finish, and in the core we can to improve the productivity you can use the 120 micron this particular beam focus diameter. 3/4 type, by keeping in mind by the experience, we came to know that once the recorder has been damaged, or soft recorder, we have to pause the machine, we have to open the machine, we have to change the particular process, and it will take so much time. So all this particular experience come into picture. We have designed all this particular bidirectional recorder, multi-blade recorder systems, where without pausing this particular with a quick change over time, we can change this particular recorder inside. And then dimensions and weights are there machines. Second machine, by keeping in mind all IIT, all institute, all this particular dental industry, all medical industry, and then just now, if I'm not wrong, Colonel Kober has asking one question about this gold printing also. By keeping all these particular minds, we have developed a small machine. Definitely we are going for this particular certification, all kind of things also. This is a build volume of diametrical 180 mm, with height of 200 mm. We have given 200 watt laser also, 400 watt laser also. It is optional kind of things. And then scanning speed is up to 5 to 7 meter per second. Here, by keeping in mind the small product, we are focusing but particular layer thickness of 30 micron to 60 microns. Same recorder time, recorder is we are proposing here, and then dimension and weight you can see, and then the what we developed our machine, it is powered by Materialize. The Materialize, what they have given, it is a particular magic software, support generation software. Apart from this, all this particular our machine is bundled with perpetual license of Materialize Magics. And then the print control hardware and software developed in the collaboration with Materialize. All this particular build processor, what are this particular strategy to print, means the meander pattern, stripe width, then particular laser power, and then scanning speed, all the process parameter developed for each and every material. We had collaboration with Materialize, we have developed with Materialize. And this machine design, what are the machine we have designed with our own experiments, means XYZ calibration, this recorder calibration, and then the loader calibration. Apart from this particular part calibrations, all we have machine design and configured and validated by Materialize team from Belgium. The AMG advantages. Just now in previous slides, I had touched these particular things. There's a big advantages. Over 60 service centers we have across all over India. Almost 250 service engineers are there in this particular service centers. Meantime to respond all these particular our existing customers. What are our 70,000 plus existing customer of Asymmetric Group? Meantime to respond is less than 4 hours, and locally available spare parts because we are present each and every city of this particular Indian map. And then service team from the factory available with short notice. We, apart from this, we have the 9 tech centers with AM experience zones, where you can see our particular machine. You can go, you can taste this particular. You wanted to print some parts, and then definitely in the tech center, definitely in future, our each tech center we have the one machines available in future also, where definitely you can taste our particular check. Your print capability, and print qualification also. As you know, we all came from the research and development background. All this we are doing this continuous research in collaboration with academia also. What we have started with the industry academic collaborations, and then we have tied up with multiple technologies being developed with association with all this university. Not only powder bed technology we are focusing, we are also focusing up all other technologies available, just like LMD, DD, all we have tied up with each and every university. And definitely in future, we will give you one-stop solution for this additive manufacturing metals. Definitely in future, AMS will be the one-stop solution. Whatever you want this particular in metal, definitely all the machines will be available in the AMS. So conclusion, okay. It's a high productivity printing parameters with volume mate. We have developed our own build processor with this particular high productivity parameters. If you definitely want to go to jump to 120 micron with high quality, definitely we will give this particular things. Dual laser. Already I told you we have the 1 kilowatt 2 lasers. If the customer is want, definitely we are working on the quad laser also, and then the bigger platform also. We have some future plans. Rich building a machine experience. Almost last 60 years we are developing this particular kind of things, and then definitely we have almost up to 70% repeated customers are base are there. Definitely we have the rich building experience, and then we have the global presence also in the American market also, and locally available spare parts also there with the service engineers. I already covered it this, and then the faster ROI this particular machines. So apart from that, we have the two machines. Is STR 400 by 400, and one is a smaller machine 180 diameter. So hope I covered this. Yeah, it's the last slide. Thank you all of you.
Thank you so much, Shreyans. I think we wish Amaze a very future. I mean, you already have a long vision of coming up with various other technologies also. Now that you've started with the binder jetting technology, but I know that you have a long way to go, and the way the company has been able to structure itself for last 5 decades. So wishing you all the best. And I'm sure when it comes to anything to do with the technology, all the participants can definitely reach out to us, and we will definitely want to connect with Amaze. Amaze is also our 3D Graphy corporate associate member, and our conscious effort is to actually also lead the channel to see that how these technologies can get proper proliferation for the end user to benefit from that. Thank you so much.
Yeah,
Shreya.
thank you all of you.
Thank you.
Thanks.
And may I now ask the next presenter, Mr. Chandan Mishra, who is also the company is also a 3D Graphy associate corporate member with us, and we also want to see that how new developments through Lodestar, where he is the director, Lodestar Innovation, where we also get to know that these technologies can be really benefiting the end user going forward. So he will share his presentation on the subject. He will be dwelling upon polymers basically. May I ask Chandan to take the presentation through. Thank you so much. Chandan, I think you're out. Yeah, I think he's lost connection. He should come back. Yeah.
Looks like. Are you?
Yeah, Chandan, you can share your presentation slide, and then you can start, please.
You able to hear me?
Chandan, I think slight lag from your side. Can you just report it?
Are you hearing?
Because the network is copying the sound. You're breaking in between. That's the reason.
Are you able to see my slide?
Yeah. We can see the presentation slide. Yeah. We can see the slide. You can continue now.
And you could hear me well?
Yeah, we can hear you, but it's breaking in between.
Okay. I think it's. try. So since morning, I think we have very wonderful sessions with many industry veterans. Talked about a lot in understanding relevant processes, certification challenges. I would go to spend some time in helping understand how is the polymer aspect of additive manufacturing is adapting to special deviations. A quick background about Lusta. We have been a solution providing company from medical polymer, and Dr. Monat spoke about EM and EM process within some components, which are engine components. I think he has covered it so eloquently in a short period of time. I don't need to explain. As we represent GE additive for the EDM-based product in India, helping bring that technology closer to users as well as providers and other institutes. Yeah, I'll spend more time having understanding polymer and necessary high performance polymer which are used.
Chandan, I'm so sorry. Chandan, excuse me. Chandan, you're breaking in between. It's not fluent. Your voice is not fluent.
Oh.
I don't know if the others are also facing the same problem. I think so. Captain,
I think you have to help.
Yes, there is a break in your voice. There is.
Oh yeah, okay.
I think Steve, if I need, then probably have to check the network.
Okay.
And
so then can we proceed with the next speaker and then have you on board subsequently, Chandan? Okay, so you can keep trying nevertheless. Yeah, you can keep trying nevertheless. Yeah, and then you can join subsequently. Thank you so much. So if I may ask Dr. Paul to then join for this presentation. Doctor, are you around? So why, in the meantime, Chandan will also sort his internet thing. You can join. Thank you so much. So let me introduce you to Dr. Paul. Paul happens to be a key respondent in additive manufacturing for almost 2 decades. He's also been a researcher and he's been a key faculty in RRC8T. And interestingly, they've done some fantastic work, and he's also made an indigenous machine, which is an EBM technology. And very proud to know that, Doctor, yesterday in detail when we discussed of all the good work that you've been doing. So I'm sure it will also encourage our conscious effort to work with institutes like yours to see that how training and education can be a lead, and also then to benefit companies to probably procure these technologies, maybe partnering it in collaboration. So as we discussed in the morning, Wing Commander Ramanji also mentioned about the prospects of looking at an investor panel. You did also mention that with grants, you're also looking at that kind of a model. We can definitely see into that subsequently, eventually. But yeah, before that, I think we will also have your share of insights to be shared. So I think we will take it to the next course. Thank you so much, Doctor. Please, you can start your presentation.
Thank you, Dr. John. Is my presentation visible?
Yeah, I can see your slide, Doctor. Right, you can start.
And voice is also very clear, right? Yeah. So yes. Good afternoon, everybody. It's a bit late session, like things are going a bit delayed. So many of the things which were basics I removed, and I tried to focus on the main agenda and try to bring the things so that at least we can use the time, and at the same time we should try to catch up the time in the session so that it is useful to bring back into the track and complete the time part. So let me introduce what RRCAT is. Most of you must be knowing, but still for completion, let me tell you. Rajaramanna Center for Advanced Technology is a premier R&D institute under Department of Atomic Energy, Government of India, engaged in non-nuclear frontline research areas. Like we are working in the lasers and we are working in the particle accelerators and related technology. When I talk of the lasers, means any laser which is built anywhere in the world, you will find a scientist working on this lasers. And if you talk of the particle accelerators, any advanced technology, if you talk of ultra high vacuum, if you talk of RF technology, or you talk of making niobium processing, or if you talk of managing the high-end stuffs together and making a high-powered magnets, everything is being done here at RRCAT. We are about 1570 employees with 60 external PhD students. We offer 140 plus MTech projects every year. And as far as the PhD is concerned, we have almost equal number of people registered from the department size. We are also Constituent Institute of Homi Bhabha National Institute, a deemed to be university under Department of Atomic Energy. You can join us through BRC Training School at RRCAT. If you are a PhD, having very good career, came up with very bright ideas, then you have the opportunity to join us with K.S. Krishnan Research Associateship, which eventually you can be absorbed by the department after 2-year work. You can also join PhD program at RRCAT. We offer a PhD program in engineering physics, life sciences, and engineering sciences, specifically in mechanical engineering. We also offer orientation course on accelerators, lasers, and related science and technology. It really gives a flavor to the PG final year students. If they want to pursue their career in the research, they can have a flavor how the research is being done in the country and how the things can be taken on the next level if they wish to proceed in the career. Let me come to my lab. We are working at the junction of advanced design methods, material science, manufacturing, and material processing techniques. And we are covering full domain from system design and development to material processing, to material testing, to qualification and validation, to multiphysics modeling. So that area that we are working on, and our efforts to have a research endeavor and collaboration so that we can make groundbreaking high impact results and create innovative lab technologies. So that is our mission, to go ahead with us. This is a team. I have a pretty good team, about 16 people full-time working with us. And I'm showing the partial list of the students. These are the 4 students who are working full-time with us. They are PhD scholars. Equal students are being shared with other institutes, for example, IIT Indore, IIT Kanpur, IPR Ahmedabad, and IGCAR Kalpakkam. So I have 8 students working on laser additive manufacturing technology in our lab, beside the 15 full-time employees. This is our research effort, because when I was going through various aspects of this, I realized there is a need to have a textbook in the market, and especially written by Indian authors in Indian style. And I'm happy to share during the lockdown, when there was a lot of tension and pressure, why should not we utilize this time and write a book? So last year, when it was locked down for the 3 months, we could write this book, and it has come very nicely now. And it is now available through Amazon and Flipkart. And to make it competitive in the price, we went to the Macravels, and the price is also brought down to near 700 rupees, so that it is a very good and available information for the people to work on. And it comprehensively covers all the syllabus proposed by AICTE and all the leading academic institute in the country, as well as it has got a flavor of the experience that we earned in last 18 years while working in the area of the additive manufacturing. So with this background, let me tell what we are doing at RRCAT, especially in system development and component development. And then quickly I'll go to the technologies, challenges, and then summary. And I will not touch a specific part for the design for additive manufacturing for this time because of the scarcity of the time. But again, I will try to bring the things in between so that people we will discuss about, and we have a comprehensive look about the technology. What we did is we developed the 2 kilowatt fiber laser based DD system, and this system is I think there is some issue. Just a minute. Yeah, no problem. Yeah. So this machine is 2 kilowatt fiber laser based system with 5 axis. We have used Siemens 810D controller so that it is easy for industry to adopt. Volume size is 250 by 250 by 250. It can use wire from 2 to 20 meter per minute. Wire diameter can be 1 to 2 millimeter in diameter. And it is also used wire powder from 2 to 20 gram per minute. And this is really fantastic technology that we have developed. And now we are moving this technology to next step, to giving to the industries through our incubation process, because we have been recognized as one of the leading incubation centers in the country with the declaration by the Honorable Finance Minister on 20th May 2020. So we have incubation center in which industries can come work with us, try to have a taste of that. And to give a flavor of that, as a first part, we are offering services, for the additive manufacturing. So initially, people can come, give the parts to us. We can make for them, work on the design for additive manufacturing part, make the things happening. And once they have a feel about the machine, definitely the technology can be taken by the industry so that we can go to another level. In the morning, when there was a discussion, there was a point that the machines available in the countries are limited to 1 meter by 1 meter by, is a 400 millimeter by 400 millimeter. But I would like to say here, the machine at RRCAT is not limited to 400 by 400 by 400. We have a DD machine working for 1.6 meter diameter and 1.4 meter length. Especially this machine is built seeking the requirement for the nuclear program that we have in the country. And this machine is now working very nicely, and things are being done, whatever the machine heads we have. We have a plan to add not only working with the 2 kilowatt machine, but recently we are upgrading our lasers to 10 kilowatt laser so that we can have a larger beam size available, speed can be done, largest component can be built, and many other features are being incorporated in this machine so that we can have a really big innovation coming into the area of LAM DED in time to come. Another endeavor, we built a powder bed fusion machine on the 500 watt fiber laser base. This machine is again fully indigenously made. When I talk of making indigenous machine, it's not buying the component and assembling that. It's a making a full machine indigenously, getting all your own GUI made, making your spreading unit made. Everything is from India. And now, after getting a very good hands-on, we are trying to figure out where the problems are there, where we should work on. And recently, we are trying to match and make some of that things so that we can reach very fast to the next level, and very soon, maybe in a year time, this technology will be again available for the incubation to the industries, and the industries can think of taking this technology and take to the next level. You see, this is the open part of that. You might have seen this is the indigenous machine part, how the things are building here that I wanted to show you. You guys see how the things are being on this machine quickly. Again, the working volume, presently we are using 250 by 250 by 250. Again, here the galvano scanner is presently from a scan lab, but our own indigenous galvano scanner is coming very soon, and people are working on that. Layer thickness, most of the people are working up to 100 microns. Here we have a target to go up to 250 micron layer thickness. How can it be done, and how should we proceed ahead is the matter of the strategy, and our team are working in this area. Now, let me tell you about what the recent works we did in the LAML, specifically in collaboration with so many lead institute. If we talk of BRC, if we talk of IGCAR, we talk of IPR Gandhinagar, ARCI Hyderabad, Vikram Sarabhai Space Center, definitely Dr. Anil Kumar is one of our close collaborators to make the things happening for ISRO programs. Then we have IIT Indore, IIT Bombay, IIT Kanpur, IIT Guwahati, IIT Palakkad, and many NITs. So I have around 32 institutes working with us on the different projects, and we are pushing the technology to another level in the country with the help of the academia. This is one of the finest job that we did for our program. See what was happening. This is called Delero 50 bushes. These bushes are used in control drive mechanisms of a nuclear reactor. Specifically if you talk of nuclear submarine, if you talk of ground reactor, we always have a control drive mechanism to control the reactor reaction part. And in that particular thing, the people use something very small component like bushes, and these bushes having a problem of galling. And to reduce the problem of the galling, this has to be made of either Delero or columni alloys. So that is the thing that people try to work on, and we have to focus on this. So what our friend at IGCAR were doing is, they used to take a stainless steel substrate like this, and they used to deposit Delero 50 or columni using GTAW on that. They used to machine in and out to give the shape. And what the basic issue here was, Delero 50 and columni 6 is very hard material. The hardness is more than 850 VHN, and it makes the life very miserable. And because of the galling, they cannot afford to have any dilution zone in the material. So it was very difficult task for them how to measure it. And they were taking almost 45 days to machine in and out and making the things happening at IGCON. What we did is, with the DED machine, we built very simple, giving by helical upward motion. And after that, we did the machining in and out. And as a result, thing was reduced to 72 hours. So this is the magic that we are talking of doing. We're using DD technology and additive manufacturing technology in the country and abroad. Another beautiful example is making a mesh type spacers. These are used in fuel cluster simulators of 544 megawatt pressurized heavy water fuel bundle. And in this, what is happening, you see, this is a very nice component. The dimension is about 120 millimeter diameter, height is about 10 millimeter, and the thickness, we are talking about 1 millimeter with 100 micron dimension tolerances. So people were working on this part, and a lot of issues were there. And earlier, what the conventionally people were trying to do is, they used to do wire cut of these shapes. And you see so many square and triangle and circle, and it used to take almost 7 working days to make one mesh type spacers using wire EDM. What we did is, we started making this using a powder bed fusion technology. And after that, this 7 days is reduced to 2.5 days. So that is the thing which we wanted. And what was happening, this particular project wanted 56 mesh type spaces. And with this our supply, the things made a big change in that, and they could save almost 3.5 months time in their project schedule. So that sort of thing we are talking, how the laser additive manufacturing technologies is making impact into different applications. Another beautiful example is making honeycomb shaped orifices for prototype fast breeder reactor. This is the component which is used for as a pressure drop devices to facilitate uniform temperature distribution and flow of liquid sodium in the reactor. So this is again, we built with LAM technology. Earlier people tried to make it many conventional technology, including GTAW, conventional casting, investment casting, but success were limited. When we did this, things are going on. Now all of the lot is being planned to build using LAM technology. Another beautiful example, already Mr. Mohan Kulkarni talked about making heat exchangers. Yes, this is a beautiful example, one of the things we are doing. And these things are basically focused for generation 4 nuclear reactors, very compact things which is going to come in future. And the first prototype they are expecting to shown by 2030. And many of the solar thermal energy generation part. And all these things will be used in supercritical CO2 Breton cycle based stuff. And what the idea is to have a compact thing, low pressure drop, high effectiveness. And again, we built one prototype of 200 millimeter by 200 by 150 millimeter using our present technology. And what was happening in a few, conventionally, these things are built by using printed circuit heat exchanger technology. And in that, it is costing around 70 lakhs in Indian rupees if they buy one unit. And we are able to build this in 3.5 lakh rupees. You can see how big the price difference is coming on this, and the technology is more environment friendly as compared to the printed circuit technology. So that is making the difference, and we are expecting some 400 units will be required by 20 to 30. And once you go for the 400 units, you can think of how much saving we are talking when we talk of using this novel additive technology in the domain. With the post-Fukushima, we had a lot of pressure to improve the safety and security of reactors. We are also working in making a more reliable reactors, specifically in Zircaloy 4. We are working to try to deposit silicon carbide clad layers on Zircaloy 4 tubes. Some of the initial experiments were done. We have really good success, and things are under process. So here idea is, why should we have only Zircaloy 4 tubes? Why should not we have some silicon carbide deposit on this, so that the temperature resistance stability of the tubes can be improved drastically? And this is bringing a big change into the nuclear technology in the area. We also worked in depositing copper, specifically using DD technology, which is considered to be difficult to work on. And this particular stuff is one of the requirement for our applications, specifically when we talk of in situ sensor making. We are talking of making sensor on the component itself. And can we have a dissimilar material junction made using DD technology so that things can be done? And what I'm showing you is the basic results and how the things have come, what was the strength about it, how the microstructure and other things are coming, which is in the public domain. But again, the whole technology is to make in situ sensors using material like copper and copper nick and inconels so that thing can be brought to another level. We are also working making the stainless steel composites in the collaboration with NIT Warangal we worked on. Can we have stainless steel mixed with the tungsten carbide so that our performance can be improved? Some of the work is done. It's already published and available in the public domain. Another beautiful example of work is making functionally graded material using LDED. This is the work we collaborated with IIT Kanpur and Institute of Plasma Research. And here objective is to make a deposit molybdenum over copper. And this is the thing which is going to be part of ITER project in France. And we know that in France we are making international thermonuclear reactors, experimental reactor over there. And this particular part will be made and the component name is plasma driver plates. And idea is to have a 0.5 or 0.3 millimeter thick molybdenum coating upon special copper alloys. And we started depositing on that, and we found that things are not happening. Molybdenum cannot be deposited directly on the copper. So what we did is, first we deposited nickel on the copper, and then we deposited molybdenum on the nickel. So that sort of technology, we started working on it and established the stuff. Now component is being fabricated in our lab, and soon this will be dispatched to IPR EPSOS 22 ITER for the characterization and testing. We are also making functionally graded material of stainless steel and Deloro 50 for some of the novel applications for the PFPR reactors, and things are going to be make big change in that scenario also. We always have been taught that porosity is bad. Another thing that we took into action, and then I was very much convinced, porosity is not bad, but our understanding about porosity is bad. So that made the things, and then I just thought, why should not we start making a graded porous structure? Or people are working a lot on the lattice structure part. So we did the graded porous structure. You see the porosity is increasing from 60% to 0% as we go on, and very nice space can be distribution can be achieved. And if we have very good spatial distribution available into the part, and we have high reproducibility, then definitely we can deploy this graded porous technology into various applications, into aerospace and many other where you need to have a different type of material into the place. The beauty of this particular technology would be you can have a same density material with a different apparent modulus of elasticity, which is not possible otherwise using conventional technology. You see some of the components we built, and the last one you see in the left bottom, we have a prototype hip implant made of titanium. Some testings were done. Things are again being tried and processed, and we are making things happening into the next level of the technology. So when we talk of these things, from my experience, I have seen there are many challenges for our country to proceed on. I use this forum to bring them upon, and where we should focus and make the things working into the next level. See, I decide that for us, we have 9 areas to work as opportunity. For example, machine and software development is one area, and process development, material feedstock development, design for lab, modeling and simulation, characterization and testing, controls, quality controls and assurance, application development, education and training. So these are the 9 areas. I'll take one by one these areas quickly. When we talk of machine and software development, we know that whatever the machine today we are seeing having a huge capital investment. And with a country like India, we cannot think of taking this in a very big way if we have machines available in the few crores. Now, issue is, can we have some machine built in sub crores? That makes the things different and whole ball changing game. And we need to have a lot of innovation required. At RRCAT, we are trying to build machines specifically for the academia, which can be not sub crores, but can it be few tens of lakhs, and which will fetch the lot of academic interest. So that sort of things we are trying, and maybe very soon we'll have one demo model available, and then we'll take it up to incubation and things can be brought to next level. We heard a lot about the process development and control. You saw a lot of work by us in the area of this, and across the globe, people are working on this. But issue is, can we work on a closed loop control technology, make it to next level so that a better reproducibility can be achieved? I'm not saying people are not working in this area, but still, it's just start. Things are not to the level it should have been. So what I propose is we need to focus on this. We have to bring many new tools to make the things happening in the direction of process development and control. If we talk of material and feedstock, now we have few materials coming in, and most of the material, whatever we are using, they are developed for some other applications. Idea is, can we have fine tweaking of the composition to have a better properties, or can we go for a new alloys as per the specific application requirement? So those are the areas which we need to explore and material scientists need to work on. Today we are working on design of LAM, a really thing which we are trying to do. As some of the examples are always cited that they have done full change, but if you see, most of the work done in the area of laser additive manufacturing is direct replacement type, or maybe look alike component fabrication. It's not like people are starting from that and going on, and this has to be done slowly. Things are coming into the directions. In the previous speakers also pointed out this part very clearly. We need to have a very nice established design rules and thumb rules, so that this particular stuff which is now art, can we move to the segment of science and technology, which is one of the things that we have the opportunity to work and make the things to next level. If we talk of the modeling and simulation, we all know that whenever we talk of the analytical modeling, they are not suitable for the complex structures. And when you talk of the numerical modeling, it takes very long time to achieve it. So can we use some nomogram or machine learning useful for the specific machine and the material, so that we can have a very faster and very good solutions? Our team was working one of the problems like this, one PhD students full-time working on this area. But again, we are expecting more people to work on this area, and can we bring a total very widespread modeling and simulation of the process, which make the things into different dimension. If we talk of the characterization testing, more sophisticated tools are required, as we know that, especially Microcity, Machine, and etc. In many of the applications, we need to go for the simulated load testing, specifically in our applications. So idea is, can we have some standards, some other criteria easily available made, so that these things can be done in an economical way. There is a need to have quality control and assurance, some standard like ASME section. Some things are being started, but again, we need to go for many certifying agencies, and guidelines are to be brought in. So this is again a challenge and opportunity in the area of laser additive manufacturing. There is opportunity for application engineers to come to the new domains, defining various applications, show the capacity and capability demonstrations, go for a dissimilar material processing and how the things are done, and make the things great. The last and ninth part, which is most important, is education and training. When whole country is going for another revolutions in the area of manufacturing, there is a need to have a very nice and good curriculum and faculty development program. A lot of things are being done under Atal FTB. I also am taking many of these things. But again, there is a vacuum, and industries and education institutes, especially national labs, all have to come together and make the things happening very much vibrant in the country. With this, I will stop here and complete the summary of my presentation. AM is a novel methodology capable of providing new manufacturing solutions. There is a decent lead at the international level. India is also carrying up for this. We have taken a lead role in making machine development and process modeling. We are also collaborating with different national labs and academic institutes to make the things happening faster and sooner. We need to have more innovation in this area, which is not limited to the process development and material characterization, but in a holistic way. And we need to tackle all the 9 domains for the successful deployment of the technology in the country. With this, I stop. Thank you very much for patient hearing to me. If you have any questions, I will be happy to answer.
Dr. Paul, may I ask a question?
Yeah.
Thank you for a very excellent presentation. I did visit RRCAT Indore when I was doing my MTech in laser electro-optics.
Yes, sir.
My current, this thing is on the consulting and investment. Mm-hmm. We are getting a lot of requirements from companies into working in the area of graphene technologies.
Yeah.
As you know, diamond is the hardest material, but beyond that, we also need to develop some technologies, nanotechnologies, to make the material which is light but very strong. So, can you suggest which is the organization in India or anywhere else outside using 3D technology to print material with the graphene technologies, if you have?
Sir, you know Ampri Bhopal.
Yes.
And Dr. Satish is there. He started some work in the area of metal embedded graphenes, and he's working on this area. And I think he has got 2 PhD students working on this at Ampri Bhopal. So that is the quick thing I could collect. And if anything, I'll share more details.
Yeah.
About
Please share with me. And next time when I'm in your area, I'll definitely visit you.
Please do visit. One thing I'll tell you, there is a big change in the policy by the government. By after 26th May 2020, when Honorable Finance Minister Nirmala Sitharaman told that DRDO, ISRO, and DAE should go to the public and show their technology, make it more happening in the public domain. So with that, we have many things are coming in, and fortunately, at RRCAT also we have incubation center established with the DAE framework and many things. And luckily enough, I am asked to take the lead to do this particular assignment. And I'll be happy to work with the industries, not only in the area of the laser additive manufacturing, but many other areas wherever we can collaborate and make the things to the next level of the technology.
That brings me to the second supplementary question on the technical textiles.
Yes.
Our soldiers in the army who are fighting battle in the coldest glacier in the world, in Siachen Glacier, we need to reduce the weight on the shoulders backpack. So currently the clothing is very heavy, and we need lightest bulletproof jackets and vests available with sensor. So if you or your scientists can look into that, how to make the soldier's life a little more comfortable, to make him warm but light and strong material on the technical textiles. And now that the government has already created a separate Troop Comfort DPSU out of the restructuring the ordnance factory labs, I think time has come for all the stakeholders to come together to look into this need, because it will generate a lot of export value also. We are importing quite a lot of stuff, which actually China is doing a lot of work in the graphene technology, and so is USA. So if you can kindly look into it, that'll be great. I'll get in touch with you directly also. Thank you so much.
Okay, sir. Thank you very much. Thank you.
So thank you so much, Dr. Christ Paul. It was really very informative in terms of what you've been doing, your work in the space. So training and development is also a key aspect with 3D graphy, wherein we see an opportunity to work together. And we will definitely want to connect post this event also, and in various areas that we see how we can collaborate. So now let me take the opportunity to invite Group Captain E.R. Rajapan, who happens to be a key respondent, who is also now a service provider. He's the chairman and managing director for Shivayu Aerospace. Doctor, you already have a setup and you already have offering services in 3D printing. It is more like, the extent of work that you're doing, what is that you might be looking at from 3D technology going forward when these technologists who have shared insights on each of these areas. I think it would be interesting to also have your, to go through your presentation, understand what is your current, inventories in terms of offering solutions, and what is that you're expecting going forward from the technology in terms of the offerings. Thank you, Doctor. You can start your presentation, sir. Thank you. Thank you, Captain. I'm sorry. You can start your presentation.
Just sharing the screen.
Yeah, Captain.
Dr. Shipujan, can you see the slides?
No, I can't see the slide, sir. I think you will need to upload the slide. I think the slide is not uploaded yet. So just a click, and then you see that entire screen. You just need to click that.
Slide.
Yes.
Yeah. Now your yes. Yeah, perfect, sir. Perfect.
Good evening. At the outset, let me thank Dr. Shibu, John, uh, the other panelists, and also the speakers, and Dr. John Shibu particularly for inviting me to talk on a topic which I'm not too familiar, but we are in the business to talk about what we are doing in the 3D printing. Well, having listened to the luminaries like Dr. Anil Kumar from ISRO, Mr. Manjunath from GTRU, Mr. Anthony Paul from L&T, Mr. Vaman Kulkarni from his own consultancy company, and Mr. Suru Chand, Shreya Scott, and Dr. Kaispal from RR Catch. They are all luminaries and experts in their own field in 3D printing, having contributed a lot in the development of indigenous technology and also taking it to the practical application for not only the defense and aerospace and all other fields of technology. Well, in this field, my entry is very, very late. What qualification I can call is or talk about is that I am an ex-Air Force officer who is driven by the passion for serving the nation in uniform, out of uniform. And I am also greatly impressed by Prime Minister's initiative for Atmanirbhar Bharat and Make in India. Many of my colleagues after retirement thought that it is the time for them to rest. I am driven by the passion for in uniform and out of uniform in service of the nation. I thought I need to contribute towards the contributing towards the capacity building in aerospace and defense, the field which I am very familiar with and having worked for almost 35 years, I do understand the requirement of technology and also indigenous development of many of the products within India. Even today, we are importing about 55% of the military hardware. And even after 75 years of independence, if we have not been able to at least produce half of our requirement, I think this is the time that we have started thinking how to improve our indigenous development of defense and aerospace components and equipment. So this is the reason why I also came into this field and invested all my savings from the Air Force and also other savings my family had to make a company to contribute towards India's effort towards Make in India in defense and aerospace. Well, my company's name is Shivai Aerospace Components and Molds. We are manufacturing high precision components for aerospace and defense applications, but we also manufacture components for general engineering applications and medical fields also. Our company is not a big one, it's a startup company spread over about 3,500 yards square area. And we do have state-of-the-art CNC machines, measuring equipment, and testing equipment for manufacturing and also testing various kinds of aerospace and defense equipment. Let me talk about a little about our journey so far. The company was established in 2017, and 2018 we started manufacturing, and in 2018 itself we started manufacturing components for Boeing and ISRO. Then in 2019 and 20, we got AS 9100 and ISO certification. Then some of the major DPSUs they enlisted as the vendors. They are HAL and Bharat Electronics in 2019 and 20. And in 2021, we got outreach to America and France, Tespil Aerospace, and AAA Topaz France. They also have given us the vendorship. And some of the other channel partners are SpaceNex, Cascard, Asteria, Unimed, this again an aerospace and defense company, Sika Aerospace, Sendem Electronics, which is one of the main contributors to the ISRO, Rakon, which is a French company, they are into telecom products, Walmart is a fruit product company, and V3 Technology are our other important channel partners. Our aim is to adopt new technologies and methods for developing new products for defense and aerospace application. The components we are capable of manufacturing are for the aircraft, drone, defense equipment, medical equipment, and automotive parts. And we are now concentrating on using additive manufacturing for developing the prototypes for defense and aerospace applications. And most of us know that according to research, 75% of the aerospace and defense industry leaders believe that 3D printing will become customary within the globe's aerospace and defense industry in another 9 years' time. Additive manufacturing of the 3D printing is already transforming the aerospace and defense industry, providing new ways to 3D print replacement parts on demand while reducing costs and enabling new design engineering possibilities. As you all know that additive manufacturing is extensively being used in aerospace and defense industries for reducing production costs for tools and components, provide additional design flexibility to reduce weight of the part, on-site and localized manufacturing are also be accomplished through 3D printing, and also to enhance maintenance of aerospace and defense equipment by producing spare or obsolete parts. Additive manufacturing enabler for future aerospace and defense equipment design and manufacturing. The Indian aerospace and defense market is projected to reach US 70 billion by 2030. Driven by the burgeoning demand for advanced infrastructure and government thrust, India's defense, there is a need for us to enhance our additive manufacturing capability to reach the sphere of export. India's defense budget for 2020-21 is rupees 4.71 lakh crore, which is 9.37 higher than that was in 2019-20. And this additional budget gives us opportunity for searching and also adopting new technology for developing our own aerospace and defense products within India through indigenous capabilities. Presently, only 45% of the defense equipment is manufactured in India. So in the next 10 years, if we have to become a net defense exporter, we need to adopt and also implement these new technologies, which are they are 4.0 industry as well as disruptive technologies for the design, development and manufacturing of aerospace and defense components. The government would like India to be a net defense exporter of 35,000 crores annually in the next 3 to 4 years of time. So additive manufacturing is the future enabler of aerospace and defense industry in India. Indian aerospace and defense industry is poised for a rapid growth. India's aerospace and defense ecosystem is expanding rapidly, both in the private sector and the public sector. Indian aerospace and defense industry is presently 85,000 crore. As of now, India is ranked 19th among the world's defense exporters in attracting the foreign investment, whereas India is the second largest arms importer in the world. So you see what is the difference between our present ranking in terms of defense export and in terms of imports. It is time that we have invested our resources and also brain power in developing technology within India, and the modern state-of-the-art technologies, that is Industry 4.0 and disruptive technologies, are going to be the enabler for developing this kind of modern warfare as well as aerospace equipment within India. Things are really taking shape, and if you see, in the last 5 years, we have increased our defense export by 325%. And in the coming 5 to 10 years, it is going to even grow much faster. And the government is giving a lot of SOPs, as well as they are coming out with a lot of policy frameworks for Indian private industries, especially the MSMEs, to expand their capability to support the defense PSUs and also for India's own capacity as exporters. So Indian A&D MSME's contribution is presently 18,000 crores and it can definitely go twofold, at least in the next 5 years, if we take the right initiative and also start building the equipment within India. So what are the opportunities for MSMEs in A&D manufacturing? To promote export of defense items and to make India part of global defense supply chain, Government of India has set a target of 35,000 crores in aerospace and defense goods services by 2040-2025. The government is encouraging the private sector to play a larger role in strengthening the aerospace and defense manufacturing sector. So where do we fit in Shivai Aerospace in the current scenario? Shivai Aerospace wants to seize the opportunities in the emerging AD market, leveraging the state-of-the-art manufacturing technologies, including additive manufacturing. We are scaling up to offer end-to-end solutions for various products for aerospace and defense industry. We can offer product aerospace and defense for the design, development, and rapid prototyping and serial production using our both capabilities, 3D as well as conventional machining using the CNC machines. We are also looking for JV technology partnership for 3D printing and capital funding. So which are the end-to-end solutions which are on offer from Shivai Aerospace, for which I have partnered with the Nagra Design Lab. The MD of the company is a designer who has been educated in Italy and has got ample years of experience working with major companies in the world, including Benz. So we both are partnered to provide new product design. We will also provide rapid prototyping, technology development in terms of new materials and also the products and new product design. So let me now hand over to my partner Sumit Lakera for giving a detailed presentation on our 3D printing capabilities.
So thank you, sir, for the introduction. And so as we have seen that, so already Shivai Aerospace into precision manufacturing, and it takes a lot because I'm coming from automotive industry. I worked in Tata Motors, I worked in Mercedes-Benz R&D, worked in Germany, worked in USA, and production at a precision level is something which is very challenging. Of course, many of you know it, that it takes a lot when you have to use a component on ground, and making component work in the aerospace is further challenging. So considering this capability and Nagra Design Lab, which I will show you now, I propose that we see it as an end-to-end capability, and since we are door to door in the same wall, I see that we joined Shivai Aerospace and Nagra Design Lab. We offer a capability which is very unique in the present context of the product development, and also, let's say, indigenization, if you would say, or if we say not only making a prototype, but also the next stage which comes after prototype is that we have to also manufacture it. So designing it alone not enough. We have to prototype it, we have to manufacture it, we have to again manufacture it with the same quality standards. So basically it takes a whole chain of product development to do this. It also needs an infrastructure, it also needs an experience, it also needs an knowledge. So this is what we are trying to do, a collaborative approach here, and we are in the process of doing some products. I'll quickly show you what we do. This is about me. I have worked in these companies, Mercedes-Benz, and then I did my master's in design from Italy, Milan. And so this company is about prototyping. We try to support startups, SMEs, MSMEs in developing the new products right from the scratch. At the ideation phase, we take it to a level where it can be pitched in a functional prototype format. And this is where 3D printing comes of use to us. We actually design product. First prototype itself is so functional in nature that it is used by various startups in pitching at various investment level, and it really helps. It really cuts short a lot of cost, a lot of time, And sometimes you get to know that whatever you were thinking wasn't enough. You need to further work on the design to make it better. Talking about our design capability, you can see these are all the products, all our functional products which have been working. Right, you see on the left, top left, in the middle, and what you see on the right side, Pure Sky is a product which we have done for a company, it's a startup, it's a air purifier. And so this kind of designing we are doing here. Talking about 3D printing now, coming directly to the prototyping. So all these 3D printed prototypes we have done. Like you can see on the left side is a prototype which was directly coming out of the printer. We printed in a very fine quality. And very important is that design should be I would say respected when you are going to manufacturing. We all know that what happens when we are into design, it is very fancy, it looks wow. But when we start into manufacturing, something happens in between and we end up getting something which is not so good. And I have seen this in the automotive industry, it struggles a lot. Almost, I think every industry struggles when aesthetics compromises because of certain gaps, maybe in the product design or in the manufacturing process. So this is where we are trying to build that gap, making a product which is looking as good as the design itself, and it really changes the whole game altogether. In terms of capability which we are offering here at Nagra Design Lab, which is in Bangalore, so we have something unique capability. We can do plastic parts as big as 1 meter in size. It's a very unique printer we have got, and we can do some materials like PLA, PDG, TP, ABS, nylon, and we can do some advanced materials also. And what you see on the right side of the screen is the detailing work, kind of functional prototypes we have done. Very challenging. They are directly used on field for certain functional requirements by a company, and you can see the level of detailing there. So not only the functional or looking aesthetic type, we focus here in Nagra Design Lab about the functionality of the product. It has to look good. It also has to be fully functional, and then only the whole product makes sense. That is the main ideology behind the whole concept. So these are some prototypes and the quality of work we are doing here. You can see all these are prototypes made out of 3D printing, but also not just 3D printing. We are also developing special processes for painting, for example, because 3D printing itself is not sufficient as a product, but it is a technology which basically gives you a jump from point 1 to point 2, or let's say point 0 to point 1. So we are also evolving with the different processes, different technologies, and it's a journey. And it's a journey of product development. It's a journey of research and development. That's what we are doing here. And yeah, this is what the Nagra Design Lab is about. So yeah, I think I will hand over to you, Radhika, sir, and take the questions. Thank you all.
Indian aerospace and defense product development is very, very time consuming, and mostly used the product design is being done using the existing technology and also through conventional methods. And the prototyping is one area where the 3D printing is the most useful technology. And if we have to cut down the cycle time for designing to the production of defense and aerospace products, it is imperative that we have to use 3D technology. Uh, Initially, the plastic for making the shape and prototype, and thereafter using the metal for different parts of the products. And we see an opportunity in contributing towards the design and development of the products, and the series production can be done with the conventional machines, or if the time is less for producing the number of products etc. in a one-like scenario, that is where the additive manufacturing can come into play. But as of now, what I see is additive manufacturing for the prototype and the product development. And there is a great amount of opportunity. Indian DPUC has already started using it, and along with them, we can collaborate in a small manner for the product development, the design, and as well as the development of the sub-assemblies or the components which are up to about 1 meter. This is what the Shiva Aerospace and Nagra design combined capability, and we would like to use our compliance with the AS 9100 and ISO quality standards, where we understand what is the requirement of the traceability, the material used, the non-destructive testing, the other qualitative testings which are required to pass the product. So we understand the global standard as far as the traceability to manufacturing to the supply chain is concerned. So we would like to use this experience in designing and prototyping the defense and aerospace parts. We would like to help the HAL, we would like to help the Bell and all public defense public sector undertakings. With this, I would like to conclude, and if there are some questions, I would like to take on. Thank you.
Thank you so much, Group Captain, for your insightful expression of what you do as a company. And I'm sure more than, I think, let me also introduce you as one of the key members of ADCAI. And now that Wing Commander Raman Surubiji is also here, I think it's part of the group in any which way. So very insightful. I just wanted to understand from you, Captain, beyond concept, proof of concepts, which is obviously where 3D printing technology is definitely gaining a lot of traction, because now if you want to have these prototypes and proof of concepts, 3D printing becomes a very key aspect for us to start any project. And then obviously the machining can also take over when it comes to mass production. Obviously both has to coexist. It's like science, two sides of the same coin, with machining and 3D printing. So I see that every shop floor will have a 3D printer machine going forward, and I'm seeing that the pace is also happening. But as Shivayu Aerospace, do you think that the final part production, when it comes to metal or any other material which is like a carbon fiber, are you also looking into that area of expansion to have a 360 degree? Starting from prototype, yes, you're doing a lot of work there, but to that extent, because you can probably look at having a larger pie in terms of an opportunity.
See, as a customer, there are two aspects they will look into it. One is the cost factor, the second one is the time delivery. So if they need the product in a short span of time, obviously this is one of the technologies which we can definitely use. But when it comes to producing en masse or the reasonably large number of items of the same type, then conventional machining would be better. But for the prototyping and proof of concept, definitely additive method manufacturing is the right method. And in India, you understand that we have been struggling with the designing on our aircraft for almost 30 years. Okay, the LCA project, and we didn't have the 3D technology then. Of course, it was being used in foreign countries, but our hesitation to use this new technology for the development has actually taken too long a time for us to operationalize and also fully develop this product. Now this is the time that if you want to be ahead in the industry, you got to manufacture the product within a short period of time. You cannot have 5 years, 10 years of period for development. So initial proof of concept has to be done with the additive manufacturing, and maybe few series, not series production. The functional prototypes can be with this. And there are many items which can be manufactured using the additive manufacturing technology, especially cylindrical items with the arteries and inside curved surface, etc. This can only be done through additive manufacturing. Conventional machining is so difficult. So these kind of items definitely has to be made through additive manufacturing. And we find there is a lot of opportunity, as you rightly said. In the coming days, probably each shop floor may have a 3D printer. It may not be the sophisticated one, but to get a feel of what is going to be the final product, at least the shape and other things can be seen. Visualization per se is definitely possible through the additive manufacturing. And we in South India, we would like to be one of the major contributors, though our assets are not big, but definitely we can scale up if we get continuous orders. That is the reason we want to partner with the people, and we are willing to collaborate with anybody who's interested in collaborating with us. And also our combined experience in the manufacturing and the 3D printing will be offered to them for their business and prototyping, proof of concept, whatever they want.
Yeah. So I think collaboration is the key, sir. As you rightly said, even if you're not looking at immediately procuring the metal machines, these are large size machines which can print metal. I think there is an opportunity in terms of even collaborating with these service providers in terms of seeing, how those capacities can be, dealt with. And slowly and steadily, while you feel that now it's time for the organization to even set up a metal machine, I think that can be looked at as an option. Good. Thank you so much, sir.
We are definitely looking at that, scaling up for metal 3D printing also, but it all depends upon the business, what is likely to come in.
Yeah. Thank you so much.
We seek support for, getting that kind of business.
Right.
Dr. John, can I speak a minute?
Yeah, please, sir, please.
I had the honor of visiting Shivayu Aerospace myself about 2 years back. I must place on record that despite the COVID times, our friend from Bangalore, Group Captain Rajapan, he is from a battle-hardened soldier, has become a seasoned business person. Rajapan, thank you so much for the nice presentation and your collaborative method with the other company from whomsoever, Mr. Lakra, is the best way to go forward. In fact, for the sake of audience, I wanted to tell that ADCI is also in the business of arranging funds. But Rajapan said, no, sir, I need first orders. What do I do with the funding? But I think now you can go for funding also. And I promise that the invitation from Seattle to visit Boeing on April 11, 12, and 13 is always open. And ADCI will be very happy to take you along. We are taking some few delegates from here, India, to Seattle, and the ticket is always ready for you. Thank you so much.
Thank you very much, sir. Thank you for your kind support, sir.
Thank you, sir. Thank you for your insight and also your vision and the way you started your business, the way you have led it. And I'm sure wishing you all the best for your business, sir, and also having this nurtured and with a very effective team with Nauraga Design Lab that you have collaborated, because design is the key. It all starts with design. So congratulations and wishing you both a great success going forward. Thank you so much for your time, sir.
Thank you very much. Thanks, sir.
Thank you, sir. So now may I take the opportunity to invite Karthik. Karthik is actually a key respondent in ensuring that how this design can be matured and made real good products. So he is in the business of simulation, 3D simulation, because everything is going to be a part and parcel of ensuring that the final product is out in the market. So 3D he is actually a technologist and a technologist engineer from CAD-FEM, who happens to be a company working in consensus with ANSYS and certified as one of their assisted partners. So Karthik, you can start your presentation, and we will need to understand and learn from you in terms of how the solutions is offering better opportunities for 3D printing companies eventually, for them to also benefit from these solutions, as in the manufacturing companies. Thank you so much.
Thank you very much for the introduction. So let me share my screen. Can you please confirm whether you can see my screen or not? 1 second.
Sure.
I hope you can see my screen, right?
Yes, Karthik.
Yeah. So I think almost all of this. Good evening, everyone. Okay. So good evening, everyone. Myself, Karthik. I think I have seen a lot of presentations, people talking upon different kinds of research going on in additive manufacturing, and I do not come from that background of research and the machine technology itself. My core area is from the simulation front, how we can help the development of additive manufacturing products, especially in the metal field. So that's where I really come from, and I think I'll be discussing more on that front today. So as I said, myself, Karthik, I basically am a master's from Germany, from TU Munich in computational mechanics. And deep. So basically, we are an German company, or parent company is in Germany, and we have been working with on simulations and with ANSYS for last 35 years. So our core expertise is with respect to the simulations. As you can see, our name CAD FEM. The FEM is what we are expertised at. Not only the FEM part, but we also do the CFD, electromagnetics, optics, all kinds of simulations. You can ask for, EMAG simulations, high frequency, low frequency, and everything. Okay. So in India, basically we started in 2007, and we are basically our main office in India is based out of Hyderabad, but we have offices in Bangalore, Pune, Delhi, and Chennai also. Okay, and the main core expertise, as I said, is simulations, right? So, and that's where our customer satisfaction with the customers is quite high, because that's where we interact with the customers, help them develop their products using the simulations, and help them, with the queries they have, the support, the development processes, and everything. Okay. So today's agenda will be, I think, most of the people here knows why additive manufacturing, why in A&D, and I think what are the challenges also. And most of the time I'll be concentrating on the solutions, what we offer, and I'll be talking about the two case studies, especially from GK and Aerospace, who have built a turbine exhaust casing, and also we're talking about heat exchangers here, so which is from N topology and Synopsys. Okay, those are two case studies I'll be talking. There are many more. You can refer them on the the white papers are present, and if you are interested, let me know so that I can share them also along with. Okay, so the major challenges nowadays in the market is not only with additive, but there are different technologies which are kind of disrupting the market, starting with the chips itself, which is becoming very, very important for all the products. Then electronics, electrification is the most important topic nowadays. And for aerospace and other sectors like automotive also, the composites are playing a very important role, modeling them, and analyzing the composite and checking the failures of composites are becoming very, very complex. Not only that, nowadays people are also doing, additive manufacturing for composites too. I've seen some of the cases in Germany where they are on Singapore too, where they are doing this, and smart connectivity is one of the important factors. And then the additive manufacturing, as I was talking about, is transforming the manufacturing sector itself. As a lot of people spoke, it's not going to replace the traditional methods, but it's going to transform the processes, most of the processes present right now. And then we are talking about the Internet of Things for almost all the products which are available in the market, right? So today's topic will be mainly concentrating on the additive manufacturing. And since you see there are so many technologies coming into picture, new innovations coming into it, and to check all these things and to develop a product which can adhere to all these things, simulations is a must, and simulations is the answer for most of the things. Without simulations, I think your development cycles really go big, and there'll be a lot of wastage in prototyping, especially time and money. And if you're coming to additive manufacturing, you have to do a lot of trials to come up with the process settings, then the porosity, check the porosity, and also the material properties of it, and to check what kind of supports give you good results, or what kind of heat treatment process I have to go with. When I cut the plate, structures, then what the deformation is going to occur. So there are a lot of challenges with respect to additive, right? To address all those things, we need simulations to look into them, and we can basically address a lot of things there. So as I said, simulations is not only used in just a design and analysis phase. Nowadays, simulations can be used everywhere, starting with the ideation, where you have an idea, you want to just check whether this idea is working well or not. What we call it digital whiteboard, virtual whiteboard, where you can actually check your idea with respect to physics, whether it's going to work or it's not going to work. Okay. Then you can talk about the traditionally simulations are used in the design analysis phase. Once the idea is finalized and you develop a design out of it, and then you want to check the design is going to work for all your case studies, whether it's structures, CFD, or it's electromagnetics, or what optics, or whatever it is. Then comes the manufacturing phase, where the additive manufacturing comes. So we are also into the simulations of this manufacturing process, not only the additive manufacturing processes, other processes like sheet metal formings, Also, they are doing simulations in that front. We can do blow molding. That simulations also can be done. So we have simulations used in manufacturing process nowadays. But additive manufacturing is an exception, I guess, where people are using simulations right from the beginning to see the product and how it's going to deform because of this additive manufacturing process, and estimate the deformations and everything out of it. Then in the operation phase, yes, we have some people are talking about digital twins, where you have predict the maintenance when I have to go for maintenance of my product. Because your regular predictive regular maintenance of is not cost effective, because you may do a maintenance much before it's going to fail, or you'll do maintenance much after it's already failed. So you want to, instead of going for a regular maintenance, you want to predict when I have to go for maintenance, right? So digital twins are the technology which helps you in this aspect. Then we also have it in product phase, where we are talking about autonomous vehicles, where we have ADAS systems and all these things, where the software is now installed onto the cars to respond based on what comes in front of your car, based on the sensor data it's collecting and everything. You see, simulations can be literally used in every phase of the development cycle. So what we do is like, we start with the platform tools like embedded systems, so we're talking about optimizations and all these things. And we also have a material library for different materials, starting with additive manufacturing to the generic mechanical materials and aero materials, electromagnetic materials, and all these things. But traditionally, this is our bread and butter, where we do the traditional simulations of fluids, structures, electromagnetics, semiconductors, embedded software, and optical. That's where we regularly do the simulations for. So coming to the additive, I think we all know the additive, why it is really very important, and what's the advantage of additive, because the wastage is less, and you can actually combine a lot of parts into one part or few parts, so that you can reduce the usage of material. You can actually build very complex shapes, which you can't even build with the traditional manufacturing techniques. So this can actually innovate a lot of products nowadays. So that then the certification process and itself is much shorter, because you don't have so many development process of like traditional techniques. What you have, a lot of processes goes into it, and like that, additive manufacturing has very few processes. So your certification process itself or qualification process itself becomes smaller compared to the traditional techniques, right? So we have many types of additive manufacturing techniques, but for metal, basically we are using the powder bed fusion, or we are using a DED, which is the direct energy deposition, or nowadays people are also using binder jet methods for metals, right? So what we are concentrating upon as of now is these three techniques for simulation. Right now, we already have a solution for powder bed fusion, direct energy depositions, and in the upcoming versions, we are also trying to build something on the binder jet. They are working on that, and that should soon come out. To simulate the binder jetting process too. Okay, so why additive manufacturing A&D? I think the materials are very complex. The lead times are high in aerospace sector, especially. You want to optimize your products so that you want to make them more efficient, so that the weight to lift ratio can be maintained, and you can get a better performance of your products. Then the main challenges I was talking about, the supply chain and the digitization itself is. Okay, so the benefits what of additive manufacturing is, I already told you, the lightweighting itself. So you can do a topology optimization. You can come up with a very innovative shape, and you can lightweight your structure. Remove a lot of material, make it more efficient in terms of thermal, in terms of structural, also in terms of pressure drops and everything. Then you can kind of combine the parts. Make the number of parts less in your structure, so that your parts are less prone to failure and everything. So also with respect to the materials, you can also use avoid the material wastage. You can reduce the material wastage, And also you can print the parts on demand. You don't need to, store them in a, manufacture them beforehand and store them and then, spend a lot of money into that, Then the process and assembly itself is compressed, because I said that you don't have too many processes and assemblies in when you come with additive manufacturing. So because of technology, I think economic wise also your cost is kind of reduced because you're saving material. Your economic of scale also can come down. Your material wastage is reduced, and the fewer process steps, which also reduces your cost. So this is one good example from GE. I think it was done around 2018 or 2019. So as you can see, they have consolidated 20 parts into one, reduced the weight by 25%. It is 5 times more durable, and printing this or manufacturing this kind of component is no more impossible. With additive manufacturing, it becomes possible, and even the complex shapes like this can be easily printed with additive manufacturing. So with all said and done, there are also a lot of challenges coming with it. The main challenges are in two kinds. With first thing is the certification and the qualification part of it. Because when you want to go for certification of this additive manufacturing parts, the main problem is to know the microstructure, the chemical composition, the mechanical properties. Because you're dealing with the powder and then you are kind of sintering it, or you are the heat treatment and all these processes. The material properties itself are unknown. So you need to find out what is the final material properties of these structures. That becomes very important. Also, for qualification purpose, you need to keep in mind what is not only just the all these mechanical properties and all, but also the dimensional tolerances. How far is it from your actual part? That becomes very important. Not only that, you need to look at who is the supplier. What is the process you're following, and what is the machine you're using, because the repeatability and the quality of the product has to be controlled, right? So that becomes very important for additive manufacturing. In the technology wise, I think we have several challenges, starting with the distortions. We have the residual stresses, which leads to the cracks. We have build failures. We have the blade crash problems. The surface toughness itself is a problem. The durability and the porosity. And the microstructure itself, what are the material properties of it. So this all are the challenges technically, and this is what we want to address to see how we can check all these things using simulation. So what are we trying to aim is to avoid a lot of trial and error methods. So instead of lot of money wasted on them, because the cost of material itself is very high for metals, right? So you're doing a lot of trial and error method, a lot of failure in terms of the build and wastage of all these things you need to avoid. So that's what we want to do. So we want to avoid this wastage and make sure that with simulations you can get it right for the first time itself. So we can all in simulation we can do a lot of things. We can check what should be the parameters of your machine, starting with the laser power, the time, and all these things can be parameterized, checked, and we can also see what's the melt pool. When your laser is moving, we can see how depth it is going, how much of a metal is melting, and all these things can be checked in simulation. Okay. So coming to that, the traditional techniques, what we know is we know the mechanical properties. Based on that, we go select the geometry, do the processing, and we construct the part, right? But in additive, it's other way around. What we have is the powder. We need to do the laser treatment on that. You do the additive manufacturing process. Based on that, you want to check the microstructure, and based on this microstructure, you want to come up with the material properties of your material. Okay, so it's a different thing. So we need to keep all this in mind when we are kind of doing it. Okay, so what we are dealing with, we have several kind of machines which has very different scan patterns. So they have unique scan patterns, and based on these unique scan patterns, that the hotspots are generated, or the thermal, the graphs you can see on that. This is going to affect your microstructure, going to affect your residual stresses and all these things. So you need to check all those things: the strain magnitude, the defect distributions, the microstructures, the mechanical properties. So based on this thermal history and the melt pool and the full scale composites, we can actually predict what is the mechanical properties of your product. That is where we are ending up. So that's where ANSYS really comes into picture. So what we can do is we can do everything when it comes to the additive manufacturing. You're starting with the design of AM. So you need to do first a design development for your AM, which is suitable for your AM process. Then you need to come up with the build setup. What kind of support structures you need to do, how you want to space this, especially when you're talking about powder bed fusion. We need to know how many parts, how they have to be arranged so that you can reduce the time of build itself, or we can accommodate more parts into it. Then we do the process simulation to understand how much of deformation is going to happen because of this the heat which is used for sintering this powder and everything. So this is going to cause some deformation, so we need to take care of that. Then we do the material analysis. Then the main challenge is to capture all this data. We have the powder materials, we have the manufacturing process, we have parameters of machine. There are a lot of things which have to be managed, captured in a proper way, so that when you go for certification and qualification, it becomes much easier for you. So we are going to look into all this one detailedly. The first thing is as I said, in each process what we do, we talk about DFAM, which we talk about the CAD geometry, we talk about the topology optimization, lattice optimization to reduce the weight of the structure itself. Then we use this geometry, the shape which we were coming from the optimization, we convert into an STL file to build it, and we have the supporting structures, orientations and everything. Then we do the process simulation to find out the distortions, kind of to compensate the distortion so that you can achieve the final geometry what you want to achieve. We can predict the build failures, all these things. And then the material properties itself, the grain morphology, we can do the melt pool, the porosity detection and everything can be predicted. Then the management and the part qualification. Okay, so let's go in ANSYS. As I said, we are dealing with these three. The first one is the powder bed fusion, as you can clearly see. So this, we are building a layer by layer. In simulation, we can actually do this. We can actually build layer by layer, exactly what you're doing here, and can predict what are the thermal deformations coming out of it. The second thing is the direct deposition technique. So you can see that we can deposit based on the arc line, we can deposit the material on it and see what the thermal temperatures coming onto it and what are the thermal strains coming because of that. And you can see the comparison between that the simulation and the data coming from the testing. Okay, then we have the powder bed fusion. This is we have several stages here. The main challenging stage is the sintering process, where the material kind of undergoes high temperatures and it deforms just because of that gravity and other things. So we need to capture this viscoelastic behavior of your materials and everything that can be also predicted, like the shrinkage of material itself. And because in powder binder jets, basically the problem is the parts shrink by huge volumes. So that has to be considered here, and it also deforms. So that can also be simulated. So this is something which will be going to come in the next versions of ANSYS. But we have this technology for these two methods as of now. Okay. So this is the whole workflow. So this is the actual design, initial design. First, we do the topology optimization to come up with the innovative shape, which can take the loads or the application what we are looking at. Once we have come up with these loads, we can actually validate whether this can take the loads for all the nonlinearities considered and everything. Then we come up with the support structures, and then we do the process simulation, and then we do the the microstructure simulations. Clearly we can see the laser moving, and then we can see how the temperature is going up, coming down, and how the thermal strains are kind of cumulative effect. You can see that because of this laser movement on this, all these things can be captured. So starting with the first thing is the design of AM. So the thing is, you want to do a topology optimization. You want to see, let's say I have a plate, I want to fixing at one end on a hole, another end I'm just applying a displacement. I want to see which shape gives me the best result with the minimal mass and give a stiffness which can take this particular load and within the limits of stress and the displacements. So you can do this kind of topology optimization. This can be done for thermal studies, structural studies, and you can see there are two examples here. The first one is the manifold, and the second one is the housing, where you can see we are using a traditional topology techniques to reduce the weight, so it removes the volumes wherever it is not necessary. The second thing is the lattice optimization. It can actually place lattice structures internally and reduce the weight of your component. And you can also optimize this, what kind of lattice structures, what should be the density of your structure, all this the dimensions of the lattice structure, everything can be actually optimized, and you can run the simulations out of it. Once you are finalized your design, then comes, as is an example where this is the original part from a customer called Wittmann from Germany. You can see that this is the original part, and this is the final part of the optimization. You can see that the mass and volume, there's only 5% reduction, but we can see that there's a huge improvement in the stiffness in both x direction, y direction, z direction. So that is what they want to achieve, and they could achieve it with less weight, almost all 5% less weight, but a huge improvement in terms of displacements or what stiffness it can take. Okay. So next comes, once you finalize the geometry, the things what you are going to look at is the support structures. So what kind of support structures we are going to look at. So ANSYS really helps you here because the support structures are actually, you need to kind of design the support structures well, because this is going to affect the amount of material is going to be wasted. It also affects the build time, also affects the failure, it also affects your deformations itself on the structure. So all these things are to be kept in mind. So these are all engineering challenges when you go with a build setup. So you can see we have something called heat plots, which will help you come up with an ideal support structure which can suit the amount of support structures needed, the build speed, and the distortion levels. So based on these three factors, you can design. We have different set of support structures, just not this tree method. We have different support structures which can you use. And we also have the machine details like EOS, SLM, and Renaissance machine. So you can also have the laser patterns, or you can also come up with the customized laser patterns on it, which will help you reduce the residual stresses out of the structure. Okay. So once you have the build setup, you can export it out and then import it into a simulation to see what are the distortions coming into it. So you can do this kind of distortion studies. This is what we see because of the layer by layer build up. You can see where the distortion is coming up more. So this is a very good example. You can see that initially you see that this is a shape I want to print. Because of the shape, when I'm building it, it goes well, and suddenly on the top it starts bulging out. So the shape, whatever the final shape I'm getting, is not approved, or it's not qualified, certified, I would say. So then what we do is we compensate for this distortion by making the changing the shape which I have to print. And then when I print this shape, I can see that the shape what I achieve is what I really want to have. So this is the distortion compensation. So all these things can be kind of captured in a process simulation. So you can predict the distortion, avoid the blade crashes, because when it deforms more, the blade can crash in the structure. That can also happen. We can look into the stresses and strains. We can look into the build post-processing, removal of build plate. So when you do the remove the build plate, what will happen to the structure? How much is going to deform? So the support removals can also be done. Heat treatment can also be done to see what is the final stresses and strains left out in the structure. So all these things can be done using simulation, and I think you can predict, what would be the deformation or what would be the deviation from your original geometry, and you can compensate for that and build a product, which would give you an actually good result when you are printing it. Okay. So this is also is very important. You want to see how you want to place the products, how many products to plate, what will the support structures. All these things can be done quite fast, and this would give you a good understanding about how many parts I can print in one go. So you can also plan accordingly to do that. Okay. So this is one example of from an helicopter arm. So this is the original geometry. I am actually removing this part so that it becomes solid. Then I'm kind of optimizing it, which gave me a design, something of this sort. Then I have to convert that into an STL file and smoothen it out and get a geometry out of it. And then I can use this to build which angle gives me less supporting structures, less deformations. I can predict that and all, and then go for printing, and then I can print it, is what the whole cycle what we can do. Okay. Once your product part is printed, then you can actually go for the microstructures. So you can actually analyze the material. So we can check based on one bead length, we can see what's the melt pool, how much width, how much height it is affecting it. Because of this pattern, the scan pattern, what will be the effect on porosity? Based on this melt pool prediction, we'll take these results into the printing a cube, and we'll for the cube we can see what's the porosity levels in the cube, whether you have the keyhole effect, whether you have the balling effect, lack of fusion, or we are in the right area where you're getting a good density, good porosity out of it. So you can check all these things. So we can scan it for different power of your laser, different speeds you can see, and I can come up with the most optimum solution of my machine properties, which can give me a good result for me. Not only that, based on this data, I can also have a heat map on the whole structure as it's printed here. You can see that for each and every layer, I can see the heat map and analyze if there are any hot spots where it can affect the microstructure and change the material properties altogether, and try to avoid that based on understanding. Not only that, I can also do the microstructure analysis based on cellular automata method and predict what would be the grain size, what is the angle of the grain and everything. And based on this data, based on the Hall patch relationship, I can also identify what will be the yield strength and what will be the elongation of my material. So I can end up finding out my material properties, from this kind of simulations. Okay. So next comes the data capturing. As I already told you, you have a lot of information coming from your additive manufacturing, starting with what kind of powder you're using, what are the mechanical properties of the powder, to the machine details, what are the processes you are following, do you have heat treatment process after that, all these things are there. So you have a lot of data generated out of it. So we have a tool which helps you, manage all this data, and it also helps you see what processes you have followed after a few years. So this really helps you to manage and make sure that you can print the same part with all kind of settings, and you can get the certification, and you can do all these things quite easily. This saves a lot of time, and you can also have the traceability of all the features what you have and everything. Okay. So this is one example coming from GKN Aerospace, where they are trying to print the head section of the turbine exhaust casing. So the major challenge is what they want to do. They want to do the part consolidation, reduce the post-processing on the processes on this, and reduce the material waste usage and wastage also. The major this is a very good example because this part is huge. It's very complex because it has a long overhangs, and also it has varying thicknesses. So with additive manufacturing, they could really achieve a part which is within 1 mm of surface deviation from the tolerance deviation, and in some areas they could really go down to 0.7 mm, and previously they had 2.5 mm deviation, which can also be reduced to 0.9 now. You can see this is the part with the supporting structures and everything. And once the final part is done, they are comparing it with the original geometry, and they can see the deviations in every location. So this could be achieved in very short time. Now, the second thing is again with the company called N-Topology, who are into the shell tube heat exchangers. So this is the heat exchanger they had, and they want to make it more compact and reduce make it more efficient too. So they have come up with very innovative technologies, and they have a lot of triply periodic surfaces inside, which actually increase the surface area by 150%. So it became more efficient. So finally, when they kind of manufacture the product, you can see that outcome is 40 parts are kind of merged into one single part, 85% reduction in the volume, 81% reduction in the total mass, and you can clearly see that heat transfer is 1.8 times it increased, but the pressure drop also is reduced by 9.1%. So they could achieve all these things because they could use simulations to predict, understand the designs, how they are working. So also use optimization techniques to optimize their geometries, and then also to use additive manufacturing techniques to see what is the deviation from the original geometries and all these things. So I think because of short of time I had to really rush. So I hope what we believe is simulation is more than the software. Software is a secondary thing, but I think when you understand the whole physics, when you understand how to carry out, simulations can really help you with respect to your product design itself. So that's the reason why we call it a simulation-driven product development, which can really drive and shorten your development cycle of your products. Yeah. I think with that, I'll end my session. If you have any questions, please let me know. Hello?
Yeah. Yes, Karthik, thank you so much for your inputs. I'm sure, this simulations simulation does help a lot. And as you rightly mentioned, it's beyond software in terms of having a corrective measure before even you having the final part is so very important, especially when today the cost of the material and everything is so exorbitant. I mean, you need to see that, there is no wastage. And also warpage in terms of the part while it gets printed. So it's so important. And so optimization and wastage, these are again it is also a catalyst on both the ends in terms of supporting the need of the requirement when it comes to proper simulation software. And great, it was a very detailed presentation that you shared in each of the aspects where it is going to be of great importance. If there are any questions, respondents can please you can put that in the Q&A section, or we can continue with the next presentation, and you can mull over the questions. Eventually, once you have got it, you can post it. We will definitely have Karthik respond to it either with this presentation or otherwise. So we are in touch. So thank you so much, Karthik, for your inputs and your presentation. It was a pleasure connecting with you. And now that we will go to the next speaker.
Thanks, Dr. Shiv.
Thank you so much, Karthik. Thank you. So the next speaker is Rajesh, who is actually one of the key respondents whom I know personally for some long years. Rajesh, thank you so much for being here. Also, just to introduce him, he is now the key channel head for 3D additive manufacturing for Monotech. Monotech primarily is a company we started with inkjet printers, and they've really evolved with time as an organization. And I'm sure his portfolio would give you an insight of what all technologies that he's been able to get in India to substantiate and help in terms of benefit various sectors across industries, may it be dental, medical, prosthetics, orthotics, all of that has been a part, and aerospace and defense and tooling. So currently, I think the presentation would be very specific to aerospace and defense, where there is a technology called DED. We also had the presenters present in the morning talking about the prospects of DED. So I think Rajesh will be, sharing his insights on this technology, because this is more seemingly this is actually benefiting the aerospace industry. Rajesh, thank you so much, Rajesh, for your presence. Now you can start your presentation. I can see your screen; it's all live. Yeah, thank you so much.
Great, thank you so much. Thank you, Dr. Shibu, and thank you for having me on this workshop along with the eminent guests which I have seen. And since morning, there has been a tremendous amount of information which I have been gathering regarding this additive manufacturing. Many things which we learn from the industry. So the industry has told us what is required and what could be the solution. So today, the second session, of course, was about the solution for the issues or the requirements in the session one. And I would like to close with a specific technology which could transform the Indian industry to the very next level. Meanwhile, while we transform ourselves from traditional manufacturing to the pure additive manufacturing. So my topic will be selected on this, and since I am probably the end of the show, I will not take much time. I'll try to rush through so that we get into the the panel discussion quickly. So I'll just briefly talk about us, what we are, because the reason I need to do that is because we need to tell you exactly how we reached here. So it's not be going to be it's going to be a short story, but it'll be a worthwhile one. And our partnership and transformation, which we have thought about to bring AM into this industry in India, and the metal AM technologies, and the traditional versus pure AM versus hybrid. So this is a concept which we are all talking about today. We are talking about hybrid because it's between traditional and the pure additive manufacturing systems. So just a brief about us. We are established in 1999 with 400 plus employees, 6,000 plus happy customers, government, corporates, and service providers and various other industries. We started off with the 2D printing business, and we forayed into 3D additive manufacturing 6 years back. Personally, I have been in the additive manufacturing segment for more than 11 years now, and I have seen a lot of technologies around. And I, being from the equipment, the capital equipment market, and also specifically the manufacturing industry projects, I've understood that AM is the right way to go for us. And I took on, I've been sticking on for 11 years now in this industry and going strong, of course. With 15 plus locations, we make sure that our customers are all happy with us, with the type of support and everything. We also have developed our own 10 brands out of 2D and 3D, and 27 alliance brands. So the partnership and transformation which we have tried to bring into India was with these sort of alliances, which they all complement each other. They do not compete with each other. And every technology suits to a certain application. Everyone knows about 3D systems, the inventor of Sla Technology, and now today they are the only machine company with 7 different technologies. Markforged, the new kid on the block, with their composite technology and their MIM-based 3D printing, which has taken the market by storm, because most of it gets into the manufacturing industries. And bigger up with the large, platform building, and Admatec and XJet for the, for the ceramic. So we have the complete range. And then I'm going to talk more about Meltio, which is the current requirement of the industry. So just to give you an overview, we work with polymers, metals, ceramics, thermoplastics, wax, composite, gypsum. Probably something more than that. We will look at that in the future. What we look at today is that we are in the third revolution. While we talk about being in the industry 4.0, to be frank, India is still in the industry 3.0. We are still into the automation, implementing electronics automation. But by the time we be in the industry 4.0, because we are having a lot of manufacturing industries, new technology development happening in India, we would have already replaced 50% of the upgrade or upgrading the existing equipment. Now, how is this possible? Because in the morning session, people are talking about, pure AM cannot replace the traditional. Absolutely right. But it is in the process. So because today we have, high volume requirements, the future is going to be customized requirements. So the customized requirements are going to be more than the high volume requirements in the future. May it be any industry we talk about. And then that's when additive manufacturing takes over. But how do we bridge the gap is the discussion or the point which I'm going to make here. So before that, I would just like to touch upon these, because polymers, wax, everyone knows we are not touching there. We have been talking about metal since morning. So these are the technologies which were already explained in detail. So I don't go into the explanations, but LMD and ADAM, DMLS, VAM, EBM, SLM, all these technologies have certain strengths and certain weaknesses, and they do certain things, they do not do certain things. So we have to talk about how do we select the technology with the requirement of ours. So today morning, I saw Mr. Anthony talking about, more of ease of use, more better finish, etc. The surface quality has to be good, speed has to be high, resolution has to be perfect. So these are all things which are of the future. But what do we do today is that we bridge the gap. So we bring the traditional technology towards the pure AM with the hybrid system. So that's where we see that this technology, hybrid technologies, are going to be very much part of our industry in our journey from industry 3.0 to 4.0. And as we see that additive process with the machining process is what we talk about as a hybrid manufacturing process. And if we say that we combine the strengths of both the processes, basically the additive and the CNC, there are certain weaknesses of additive, weaknesses of CNC machining, but we combine the strengths of them to get hybrid manufacturing, and that's what we are doing. Today we see that the market is more of traditional manufacturing being heavier than the pure additive manufacturing industry. But tomorrow is going to be that pure AM could take over, or it could be heavier than the traditional manufacturing. But we have to find a balance somewhere. Today we were talking about, there was a question that we do not have too many resources or trained resources for our additive manufacturing. Yes, because say we talk about powder bed fusion, we need to have design for additive manufacturing. It's very important that we understand design for additive manufacturing. But how about the resources for that? We still are in the very early stages for that sort of systems. Though we have few installations in India, it's being used more for the conventional parts. I was talking to some customers yesterday in the show here nearby. They were saying that the only thing they were using powder bed fusion was for creating parts to create a business case for the industry so that they could get more business. But AM has to be utilized beyond that. So for that, hybrid probably is the right solution today, where we could actually take the traditional and the AM together. So when we talk about this, we talked about DED. A lot of presentations talked about the direct energy deposition systems, and few of them already have it, and they have been utilizing it for so many years. But we have the different type of DED systems like lens. We have EBM based. We have plasma or electric arc based. So, and we can also classify it as powder based or wire based. So when we clearly define that this is what is DED. DED could be either laser based, could be DED, electron, plasma. It could be either wire or powder. Now, when we go beyond it, we need to understand the DED. What are the advantages of DED today? The advantages are high build rates. Someone was telling that it's very fast. Within few hours, you can have kgs of parts being printed. It's dense and strong. Yes, it's dense and strong. Near net shape we get so that post processing is required and can be used for repairing. Excellent. Multi-material range possibility is there, but with some few companies where they offer powder and wire, and larger parts are possible. So size is not the limitation with this technology, and the easy material change, which is a big problem with EBM and PBF in many other technologies. But let's look at the disadvantages of DED, because of which the investment or the companies are not looking at it. We are talking about large corporates or large government organizations investing into DED, but DED should be part of the manufacturing process, and that's the biggest success of India today. If we have to be successful with our parts, products, which we need to export, we need to be ahead of, or at least at par to Europe and probably China. We need to have the technology implemented in smaller organizations, in smaller manufacturing setups. So the disadvantages really pull them back, like the high capital cost, the low build resolution, and support structures are an issue, because with DED, you do not have powder, so powder bed, so you cannot support them. Hence, we have brought about this technology to the industry today, which is Meltio. Meltio really looks very, very promising for all of us. The reason being, it's yet another DED technology, but the beauty of it is that you can combine powder, you can combine dual wire, you can combine powder and wire, 2 wires. So it's very, very flexible in terms of how it can be utilized. It's very low cost, which means that it can utilize the welding wires, which is normally for the DED, which we talk about. We can use different type of powders, and it's high capability and high compactness. So it's very compact. It's basically a laser head, which can be and the standalone machine is very, very compact and very easy to use So you do not have to have very specialized resources. Maybe probably you don't have to have an explosive proof suit to wear. And the Meltio's metal 3D process is simple, as simple as printing in polymer. So the point here is that this technology with 6 lasers, each of 200 watts, totaling to 1.2 kilowatts, can actually get you a range of materials. It can actually utilize range of materials and with whatever combinations which we think about. So now the challenge is, how do we do this? So we need to understand that the technology is there, but it's up to us how to utilize it and up to us how to test it out for the utilization. So there are standalone machines which are available with this machine technology, which give you the flexibility of testing out different wires before going with the actual manufacturing systems. So which means that you can test wires, different type of wires, open source, powders, if possible, small amount of powders, because if you have very thin details, you can use powder. So there is a powder feeder possibility. There are 2 fire feeder possibilities. So a lot of testing can be done by the universities and organizations, government organizations for different materials. So as I told you that this is possible with powder deposition and biodeposition together in a single build. So when we compare this with respect to the other technologies, DED, binder jetting, powder bed fusion, Meltio, and which I'm talking about, VAM Joule, it is somewhere in the center, which means that with all the requirements of the density, hardware cost, available materials, it somewhere comes in the between, which means it's a very good mix and a very good, it can suit to a lot of requirements of the industry today. And with the open source and different type of material capability, like we have tested titanium, we have tested Inconel stainless steel, we have done mild steel, carbon steels, stainless steels. So we have done a lot of tests on those. And further tests are on for aluminium and copper, which itself is today is a small challenge for these sort of systems, laser systems. So the beauty of this is that it's 10x cheaper, 10x faster, and 9x scalable. Now, why am I saying it's 9x scalable is because this is the only technology which can integrate with CNC and robots. Now I'll come to that. Before that, which heat source makes sense? If you see this tabulation with respect to arc, Meltio, lasers in general, in E-beam, we see that Meltio stands in an advantage with respect to the industry requirements. So we do, of course, we don't do as good as, the Meltio does not do as good as a 3D systems powder bed fusion technology, or probably it may not be as, fast as an arc, but it stands in between in terms of the speed and the finish. So just to, bind up this, is the lowest acquisition cost, large build envelope, 2 wire feeds, any number of power feeds, powder feeds, fully atmosphere controlled, hot wire enabled. So different type of materials which need preheating can be done. And when you talk about the LMD technology with respect to the graph of precision and productivity, we see that it's in a very favorable position. So the beauty of this technology is very easy integration with the existing CNC machines and the robotic systems. So I'll just run a short video quickly just to show you how it does. I will not spend more time. So you see, just
in the market. So how does the process work? The engine is connected to a deployment mechanism installed next to the machine spindle. The deployment mechanism hybrid.
I'm sorry. I'm sorry about the volume, but I can
hybrid
just,
manufacturing is an advanced process which can
show you how it prints.
which is
No, it's audible.
the laser head, which is deployed for printing.
So this is the laser
and
head,
retracted
which
for
is
machining
mounted. It's a deployment
operations
system which is next to the
automatically.
CNC.
The software generates the
spindle,
toolpath, which
and
controls
this
when
can
and how
take
the metal
almost, if
printing
it's
and machining operations
it's a
occur
vertical and fixed
in order to create the
system.
final part.
It's a VMC,
Hybrid manufacturing
and then
starts
you
with the
are
CAD
talking
model
about
of your part.
60-70%
Next,
of
the CAD
build
model is
platform
sliced to generate the
the
G-code,
UMC is
which is
universal.
used to print
It
and
moves,
machine the
so it
part.
can take
The
up more than
G-code
70
is
to 80%
executed
of
on a
the
CNC machine,
available
which
platform
communicates
size, which means that
continuously
it is
with the Meltio
really
engine
scalable.
during the printing
And
process.
this is how it prints.
The entire process can be set
So you
with
can
printing and machining
and
fully
the gas is
automated.
flowing
The
around,
result
so it acts as a
is a
curtain
rapidly
across,
produced,
and then you machine
low-cost
it. So the
final
whole
part
system is integrated.
ready for
It
your
just gets it
application.
inside the system, so you don't have to print and then take it for integration or for finish. The other thing, beauty of this is that you can do it in tandem, which means you can program it in such a way that you do some printing and then you do the machining. So for conformal cooling channels and few other internal requirements for lightweighting, a lot of things can be done in tandem. Just a minute, I'm just So the next most very exciting thing is the integration with the robots. So already with ABB KUKA, this technology has been already integrated. We are also trying to integrate it with other systems. I just show you a spherical tank building quickly. You can see how the finish of this part, and probably it takes around, say, 81 hours to do this, but you can see how it can build the whole surface without much difficulty after the integration with the. It's a complete spherical tank which you're talking about. Another is a turbo impeller. So this probably could be in, say, 10 hours or so. The beauty is that you could start from inner, go from outer. If you have a tilting base plate, you have all the access requirements without any support structures to be printed. And this is the tallest part created. It's a it's a structural beam which is being printed in hollow. So this took around 19 hours to print. So it's not as fast as arc, but not as slow as powder bed. So you can see that these are the advantages, and then it can get into a lot of industries, including casting, rapid manufacturing. So this is the win-win for the industry with this technology. And I would like to show that how this has been used with mild steel and stainless steel together in the same build, which means multi-material capability is quite possible. And all of you, if you are wondering, this is so rough, how can you get a good part? This is a finish which you can achieve after post-processing. And you can see that a lot of components, near net shape parts, this is how they look. If you reduce the layer thickness, you could get better finish. And we talk about a range of wires or materials with stainless steel, titanium, inconel, carbon steels, copper and aluminium in under testing. So I would not try to go into the ceramic printing because we are talking about Meltio, but we do have certain ceramic applications. Also, we have some technologies for various other requirements in aerospace, defense, and few other automotive and other manufacturing requirements. And with the XJet and Advantages. So I just run through this, and so we could, if anyone wants to know. So the conclusion is that the way things are being made is changing from the left, which is a complex system. We are moving towards the right, which is going to be design, print, prototype, and we are at design, print, and tools. But we are going to be there at the design, print, and product. Thank you very much for your time and patience, and thank you, Dr. Shibu, for the opportunity.
Thank you, Rajesh. I think it was a very detailed presentation covering a very large portfolio that you have with various different technologies that you are in the offering. Wing Commander Raman Surpiji, if you have any questions and about the technology, since you are a key respondent in terms of seeing how these technologies can be closely monitored and see how it can benefit the larger interest for the A&D industry.
Thank you, sir, for such a nice presentation. I am actually doing two roles in today's thing. I am flooded with inquiries from the private equity partners. Tell us which technologies, which companies we should invest. Since morning, I am taking notes. Each company, whether small, medium, large, is actually having so much of appetite for growth. And based on the presentation which Monotech has produced, I am sure you will never run short of funding. Should you have any requirement of funds, please reach out to us through Dr. Shibu John or directly with us. About a month and a half back, we were approached by a orthodontist from Ahmedabad who is also setting up a factory for 3D printing to dental plants. He said, I want to be a different doctor. I would print the dental implants using 3D printing, and he is actually now being arranged for funds. Funding is not a problem. We have a challenge of connecting the dots. Today in India, we do not know who's doing what. There are excellent silos working, both in defense, aerospace, space, jewelry. We need to put all the stakeholders together along with the regulatory mechanism. We are trying our best to see some state governments pushing the industrial partnership. Government of Telangana is in touch with us. Government of Karnataka is in touch with us. The two industrial corridors in north and south are also having thing. I can tell you that the US Asia Business Forum is launching a very big event in Los Angeles on 14th, 15th, 16th in 2022, where the large, very big investors are ready to fund. Should any of the companies here or who are not listening, please pass on a word. Fund will not be a problem. This is the time for India to grow, and I want some of you people to start thinking of how to be part of the global export. The lot of companies who are coming out of China are looking for shifting to India also. As we saw in some presentations, there is a collaboration and the market is very large. And with that, I would like to close because we are running against time for the other sessions also. Thank you, Mr. Rajesh. We'll reach out to you and we'll reach out to you very soon. Thank you so much.
Thank you, sir. Thank you very much.
Thank you, Rajesh, and thank you, everybody. Now, we missed out with Mr. Chandan's presentation in the earlier time slot. So he is finally back, and he will quickly take us through his presentation. And Chandan, we can start your presentation, please. Yeah. So again, a formal introduction. Chandan is the director with Lodestar, which is also dealing into different materials and machines. They are also into EBM technology, while they are also the distributor for GE Additive. And they also have been dealing into other materials like PEEK. PEEK also gaining a lot of traction for in the services. So Chandan, yeah, you can start, please. Thank you so much. Chandan, you are mute. You can. Your presentation is there live, but you're mute. Just need to remove your mute. Yeah. Unmute yourself.
Hello, Shibu. Could you hear me?
Yeah, now I can hear you, Chandan. Please. Thank you.
So once again, I'm sorry for the earlier trouble with my network, and I'll try to quickly do. I think we have an excellent day today covering a lot of applications, developmental work, innovations that's being brought into India. I'll try focus my presentation on adaptation of polymer, engineering grade polymer, which is specific to aerospace and aviations. That's a subject I think we never discussed, so I felt perhaps would be a good time to discuss this. During this presentations, we will have few insights of some of the case studies which companies like Airbus and others have done, some developmental work that has been happening in bringing in high engineering polymer into aerospace and aviation through additive manufacturing process. So a quick review on the requirements on the polymer. If you see high performance semi-crystalline to crystalline materials like PEEK, Ultem and PPSU, which are UL and FFA grades material required for polymer components used in aviation and aerospace. You have the industrial grade material, which are typically polycarbonate, polyamide, carbon fiber based composite materials, and your traditional amorphous consumer grade thermoplastic materials like ABS and PLA. So that's the classifications. And if you see the tip, which has the PIC and ULTEM and PPSUs, which is of interest to aviation and aerospace industry, and which is traditionally being done by the large OEMs in both Europe and US, but now has been adopted in every aspect of developmental, even functional parts, even batch productions across globe. So I'll spend time in understanding how these materials could be brought into both in prototyping to batch production for the aviation and aerospace industry applications. A quick review on the material side. So you have some of the world's leading chemical companies who have been developing 3D printing filament-based materials for these applications. You have the SABIC, which is the inventor of ULTEM material. Beside, you have the VIXREX, which is a new form of PEK material recently being approved by FAA. So you have a host of companies today globally who are manufacturing these materials, thereby making it much more available to users, companies, and service providers across the world, including in India. So just about a few of the applications, I think we saw some of these images during the presentations from other esteemed panelists. Engineering thermoplastics, which are typically polycarbonate, a PC ABS kind of material, nylon, polyamide carbon fiber reinforced materials, which are engineering grade thermoplastics being built with applications like enclosures, brackets, and in some cases, even in drone applications. Whereas the key aspect for the aviation and aerospace is the high performance thermoplastics, which includes PEEK, which is apart from the ULTEM 9085 and 1010 are the gold standard or the most required material apart from PPSU for the aerospace as well as aviation industry. Now, if we look at the materials and the new materials which are currently being introduced in the market, keeping in the demand is a material which is high heat and mechanical strength beside having the chemical resistance suitable for the applications meant for aerospace as well as in aviations. ESD grade PEEK, which is currently is one of the most sought after requirement coming from the electronics product and manufacturing company. Glass filled material for their mechanical properties have been one of the required materials, and therefore the new materials that's been recently introduced are mostly being on PEEK and the reinforced filaments. Now, just a quick overview of how is the top industry player sees that. This is one of the presentations which Curtis Carson made during one of the 3D printing conclave about a few years back, where he made a statement where he said that the Airbus has saved millions of euros by having the optimization process, including 3D printing for their component designing. That goes to prove that how much of 3D printing, both metal and polymer, has been playing a key role in improving prototyping to bringing, reducing the lead time, bringing in more flexibility into designing, being played across the industry spectrum. Now, the benefits we have, I think everyone has spoken, and in aerospace aviation is lightweight and flyby ratio factors, the certifications, both in material performance and quality aspect related to the production to the furnace. Also to bring in the ability to support the supplies of the components, which are typically a long period of supports needed on this kind of components. So a supply chain requirements also has played a key role in having the 3D printing used over the years extensively by the aviation industry. Now, a potential game changer core of the Airbus is they looked at prototyping, tooling, actual flying parts to spare parts are the four major application area. And at the same time, they looked at their core competence in building for the on-demand productions, for tooling, for skills, and the R&D. So these four applications, prototyping to the spare parts, especially for the polymer components, and therewith developing the core competence to meet these four major applications area is what has been Airbus point of view when they bring in the 3D printing to their fore and have been utilizing it extensively. In due course, we'll see some of their components. Now, a typical applications we talked about, many of the panelists have spoken about prototyping, verifications. Here, engineering at polymers play a critical role, especially when we have wind tunnel test models, when we have functional scale down versions for iteration cycle handling in the product developmental time, bringing in ability to check and verify the designs, uh, keeping in mind the timeline for the delivery of the products is a standard typical application in aviations. Apart from which you have other assemblies, manufacturing related applications where you require fixtures, calibration fixtures, workbook fixtures typically used in assembly and manufacturing stage. At the inspection, you have jigs and tools. You have testing devices, coordinate measuring devices, tools, which is where they have typically required utility of 3D printing and polymer components. Apart from which you have the stock tools where they have component holders, spare part tools holder. You have factory efficiency device tools. That's the image that you see. These are typically where they have utilized 3D printing and engineering at polymer in the applications in aviation. Now, I think I heard about a query today about graphene material development. This is one of a combination of PEEK and graphene, which has been utilized in developing a composite material for a turbine model, which is being printed on a machine which is supplied from Intamsys, and we are one of their partner in India in promoting that technology. We have the other material, if you would have seen, 1% graphene with PEEK combinations, which is also a component which is being developed by utilizing a format HD printer. This particular material was developed with a research institute combining the PEEK granules and graphenes to build this combined filament. In other direct production applications, I think Airbus has been the forefront of directly utilizing 3D printed parts for their A350 aircrafts, and they have qualified more than 1,000 parts today, which are also manufactured today through 3D printing process. Ultem 9085, which is being the material traditionally approved with FAA and other European grade certifications for material is being what traditionally used for manufacturing of most of these parts which have they're qualified for 3D printing process. If we have to look at what kind of applications where the direct production parts are currently being used, you could see some of them, like the seat end caps, armrest caps, some of the wall panel sections, some of the insulation sections used for the electrical panels. This is where these components are currently being approved and utilized and produced with 3D printing process. One of these important, and even as we speak, I think today was the news, where they have attempted to print a component in space, utilizing a 3D printing process, which is the most widely used process. We call it filament deposition modeling, or FDM, which is FFF process. So a lot of work is currently being done in finding ways to have components being made in space. As I know, there are few 3D printers which are currently placed in ISS, and work is being done there in terms of manufacturing smaller components to see if they could produce something in space. One of classic applications with NASA, they have used over 70 different component sections on their Mars rover project. Most of them polymer components were made with the FDM process, utilizing both PEEK as well as Altem material and flame retardant sprouts, housing camera mounts, large pod doors. These are the type of components which typically were considered to be produced with 3D printing process with both PEEK as well as Altem material. Another case applications of a material development. Here the client is a high-tech enterprise looking for manufacturing of electromagnetic radiation control panels. They use sections which primarily help to absorb the microwaves, and therefore they tried finding the suitability of printing contour matching such microwave absorbing material. Therefore, they adopted a process utilizing a FFF process with an intensive format machine to print, which improves both the absorbability of the material, ability to reduce the thickness of the inner parts, which enables them to reduce the overall weight, and also help them the flexibility of the system by having multiple material verification with the new utilization of the process with 3D print. Another new applications, which is what currently being done with one of our institutional customer, is where they have been evolving a material development by having carbon fiber small sections being mixed with PEEK to extrude a filament which is a composite with both PEEK and carbon. This particular material is currently under development and is being tested extensively by utilizing an intensive machine, which is a very reliable open platform systems, enabling research institutes to utilize their developmental projects in evolving this material. With this, I would end my presentations. This is a quick overview how polymer and polymer components from prototype to batch productions have been utilized even with large companies like Airbus. And I think this opens up a great deal of opportunities even in India for localization of components of traditional legacy products as well as the products which are under development for being adapted with 3D printing process, as both the materials, PIC as well as Alten, are now easily accessible. The cost of the material also have been on, which I believe is coming down, and hopefully we'll see manufacturers in India able to produce these components, these filaments, for meeting the local demands. With that, I would like to end my presentations, and once again, thanks, Sibu, and I'm sorry for the trouble earlier, and hopefully these presentations bring little more clarity into the polymer adaptation, both in aerospace and aviation. Thank you.
Thank you so much, Chandan. And with that particular presentation, I think the entire day's inputs summing up with various different technologies and materials are actually taken care, because we were really missing your presentation because that took care of the polymer side of it, because we all spoke about the metal part. But thank you so much. I think that sorted with our sorting it out backstage and then getting. Thank you so much, Chandan. I think it was more informative. I will leave it to Wing Commander Raman Surupiji. Sir, your inputs, and then we go to the panel starting in some time. Yeah, thank you.
Thank you so much for this nice presentation on the polymer side of it. Just want to know what have been your learnings while working with the Airbus Industries? What are the lessons? Hello, can you hear me?
Yeah, Chandan, you're mute. You need to unmute. Yeah. Chandan, are you able to hear? Because you're actually unmute. Sorry, you're mute actually. So you need to unmute, please.
Okay, we can pass on the message to him through email. Over to you, Dr. John.
No, he is on live, sir. One second. He was asking. Yeah, sir. Over to you, sir. Again, if you can just repeat that question, okay. He missed it.
I think
the takeaway of your experience with Airbus, because there are other panelists who are also wanting to get into that space. What is your lesson for them? I think he's got a bandwidth issue, looks like.
Yes, sir, I think so.
Please carry on.
Earlier. Yeah.
Please take over.
Yeah. So we will be starting the panel discussion in some time, just to sum up our and conclude in terms of what the aerospace industry is gearing for, and what are the solutions that is being offered, and where we can set a pathway going forward. We will actually move on to the panel discussion. That's the next session, gentlemen, so that we can start. Thank you so much.
I would like to announce that we will be present at this Defense Expo in Ahmedabad in the month of March. So I request all the speakers to book their tickets for Ahmedabad. We would like to have one small technical session dedicated to 3D printing industry itself. So if you haven't booked your tickets to Ahmedabad, please coordinate with Dr. Shibu John. We may like to have a small display space also to all the members of 3D GRAPHY and ADCAI. So please reach out to us. We would like to issue the directory and send it to the 85 countries with whom we are in touch with. We are being approached by various embassies from USA, Canada, France and other places also. What is the initiative by India and Indian companies? So we would like to connect the dots. And while some of you are doing great work, small MSME are not able to reach that space, we would like to encourage you to please share 2 or 3 slides of each of the companies. Reach out to us We are compiling a huge database of around 10,000 companies in India. Out of that, very soon you'll find the top 500 and top 100 Indian companies being listed there. So please submit your inputs through Dr. Shibujan directly to me. So we would like all of you to get listed in the directory, and the first copy of that will be going to the Prime Minister's office. Thank you so much. Dr. Shibu, over to you. I think Shibu is preparing for the next session. Any thoughts, Dr. Sarup Chand or anybody else? Do you think there is a need for listing the Indian companies who are missing the bus?
Very much, sir. I think it's a good initiative, and it would help, and it would list down some of the manufacturers of 3D printers in India. So you may like to do some classification of the manufacturers and their
Yes.
technology
Yes.
and their experience in materials. And there may be some other people who are service provider and the type of services which they have been providing in the additive manufacturing.
Absolutely. We also want to list out the people involved in the 3D printing training per se. I am
Absolutely.
of the view that government of West Bengal has got a company, state government undertaking called WEBOL, West Bengal Electronics,
Yes.
who are doing training in 3D printing. I am not sure there's anybody else doing, but of course Bangalore has got a lot of startups where we'll request Group Captain Rajapan
I am
to.
just answering questions.
Yeah, so we would like to connect the dots,
Sure,
and
sir.
nobody should miss the bus. It is India's turn now to reach out to the world, and then friends from RRCAT and anybody else, space, nuclear, anybody else would like to compile a directory and see. There'll be some people will miss the bus, but like the Economic Times brings out the top 500 companies, or the Defense News got top 100 companies, we want a India directory of 3D printing to be brought in. We are working on a similar project for the aerospace defense industry also, because ultimately, individually, it's very difficult for a company to reach out to the regulatory people also. We are in touch with at least 7 state governments who are looking forward to, creating investment forum also. So we would like to say, what are you doing for promoting the 3D printing? So
Sir,
Uttar Pradesh government has got. So we would like to have it done. So with that, hand over to Dr. Shibujan again.
yeah, sir, we will need to go to the panel discussion because people are
Yeah,
waiting
please.
there. Yeah. So
Sure.
we'll have to come out of this session and then go to the panel discussion session. Yeah.
Thank you so much.
Yes, sir.
Thanks,
Yeah.
everybody.
Thank you so much. Thank you, Captain. Thank you so much.
Guruban Rajapan, you are in the factory. We can see some machining going on.
Yes, sir, of course.
Good. If you can somehow use some, sheets to reduce the noise.
Okay, okay, sir. Sir, how's the sound reduced, sir?
Yes, reduced. And then only when you are speaking, that time you can unmute yourself. And I'm very happy that at least people are working on Saturday also in your office. Good. Unlike France or Germany, they are now shifted to 4.5 days of working. So in India, we work 8 days a week, or 7 days only.
For me, it is 24/7, sir.
So Ramanji, we are waiting for you in the panel discussion. We're just starting because
Sir,
yeah.
I am there.
No, you are not. You are there in the session 2. We are still in session 2. We will have to move out from here and go to the panel discussion area.
Dr. Shibujon, am I there? Click the panelist